Always good music.
Nice. Love it. Awesome. So welcome to HashiTalks Build 2024. We are so excited to have you all join us here live. I'm Bruno Schaatsbergen. I'm a developer advocate at HashiCorp, and I'm accompanied by colleague and co-host Kareem Saterli.
Also developer advocate, and excited to have you all here.
Nice. So HashiTalks Build is our virtual community conference focused on you, builders, creative people with creative solutions using HashiCorp products. And we have a day full of great content for you. But first, a few notes on housekeeping. And to begin with, our code of conduct. We are committed to making HashiTalks a safe space for everyone, everywhere. So please be respectful, welcoming, and kind to each other. And you can review our code of conduct at hashicorp.com community guidelines. It should be down below here. But with that, let's get started. We have speakers lined up for you from all over the world, talking about building a good UX, state migrations between AWS providers, creating self-service infrastructure platforms, tracking modules using a module log file, surviving a monorepo mess, and a lot more. Kareem and I are super excited to be the host of so many awesome speakers today, and we hope that you're excited too. Now, our first speaker is going to talk about something I wish more companies would look into as well. Incident.io has set the bar high on this. Kareem, what makes a good user experience to you?
I think anytime you have a tool that thinks along with you instead of getting in the way, that's really where UX and developer experience really shines. And I'm super, super excited about this next session.
Nice. Chat, give it up for our first speaker, Rory Malcolm, who's going to talk about building an infrastructure as code flow that works alongside, not against, your dashboard user experience.
Hi, I'm Rory Malcolm. I'm an engineer at Incident.io, and today I'm going to be talking about Terraform Aware, how to build an infrastructure as code flow that works alongside, not against, your dashboard user experience. The base of this is a bit of work that we've been doing recently at Incident in order to sort of make our dashboard no longer just something that Terraform configures remotely, but something that is intimately aware of how our users are using Terraform to configure our product, and makes accommodations to support that as a first-party interface into the configuration of our product. So who am I? I'm an engineer on the on-call team at Incident.io, and Incident.io is an incident management provider that lets you run smarter incidents from start to finish. We have 3 products. We have our incident response product, which is called Response. It manages communication throughout your organization when incidents are occurring. So this does things like allows you to notify the customer success managers that are the people that are impacted by the affected customers. It lets you pull the right teams in when you need to. It lets you share incident updates through to senior management when they need to. That's our product for internal communication and incident management. And then we have our status page product, which allows you to communicate internally, publicly, and privately to customers when your service is having issues, and it lets you give them updates promptly when that is occurring. And then finally, we have the product that I work on, which is On-Call. On-Call is our paging product that lets you get the right people in the room when it matters. We support scheduling, escalation paths, alerts, and all that sort of good stuff. It basically allows you, from the first time an error fires in production, to bring the right people in immediately and escalate up the tree when a problem becomes larger than just something that requires one engineer. So where does Terraform come into this? So we've long had a Terraform provider since some of the earliest days of the company. Everyone here is a long-time user of Terraform and likes Terraform and understands how Terraform works and what we think is good when we're building for Terraform. But our provider for a long time only supported a subset of the total configuration options that are available to you with Incident. Some of our more complicated products were things that we didn't support yet. So There's things like workflows and on-call, and there was a whole load of like the product surface area where customers were like, we love that we're interacting with incident using Terraform currently, but we really like it if we could do more, right? Like I'd like it if I can manage my whole incident configuration in Terraform. So as part of this work, we started thinking about workflows. So workflows are one of the most powerful parts of our product, but with power comes great complexity, and they basically are, it's a workflow engine, right, that allows you to customize incident to your organization's needs, right? And this allows you to, in response to a whole number of events that can occur with incident platform, allows you to conditionally and logically take actions within the incident platform in order to achieve the goals that you want, right? So this here is one that I've taken from our production account. When an incident is created or changed, and it's major, we invite the customer success managers to that channel. So this is just a simple little workflow that shows the sorts of things that can be achieved in an incident, but this has become like a core part of our customers' response operations. People use it to page the teams that they need. There's a whole load of things inside of workflows that are mission critical, right? And we treat any sort of like modification or code change to workflows as an incredibly important thing. And we've spent a long time making sure that the workflow editor allows you to express this complexity in a way that's safe. So for example, these are some of the configuration options, and each of these introduces new logical and sort of security constraints on what we can do with workflows, right? Like we want to, when a workflow is about to run on a private incident, which might have sensitive information inside of it, we want you to know that that is what you're doing, right? Like you are going to be inviting people to this private incident channel. And currently within the dashboard, we've had like a long time of dealing with workflows, and we think we've managed to get workflows into a space where they're usable in a safe way. And if we're going to expose those via Terraform and the way that people interact with it via code, we need to have like a bit of a think about that to ensure that like what we're building here for workflows is correct, and that the UX is as sort of as safe and as familiar to a user as it is via our dashboard. And then at the same time, we were working on on-call. And there is a level of like expectation that users have around using infrastructure as code to manage their on-call resources that we just knew that we had to support it, right? Like we couldn't not get away with, but like we didn't want to have customers in this halfway house, right? Where they wanted to Terraform their schedule operation, but they couldn't, right? And because we didn't support it yet, so we knew that on the release of on-call incident that we were going to have to support the management of schedules via Terraform. It's critical technical and business infrastructure. People want to manage this thing in code. They want to have the authorization in order to make changes here, so that their like business operations can't be impacted by some user in the UI that they have no sort of like audit log of how that's occurred. But similarly, it's like really complex, right? Like this here on the right is a follow the sun schedule, which as the sun goes over the earth, new people come on call in daylight hours and then rotate off, right? And this is 3 rotations are required to support this, each for like each of these geographical regions. And although this is not the most complex schedule in our interface by any means, it still becomes unwieldy to write the specification out for this in an API response. And there's a whole load of parameters that affect how schedule calculation works. And when you're providing a user with that to get them up and running, you want to make sure that they have the easiest sort of job of doing that as possible. And when we are writing this in infrastructure as code, like these are some of the most complex resources that I've ever applied in a Terraform apply. The problems we have here are shared, right? So like in both of these circumstances, we have parts of our system which we have been enforcing a walled garden for, right? Like we've been making sure that users manage them through the way that we built, and we spent a lot of time in order to make sure that our dashboard interface for doing this works and like feels great. And as we're sort of exposing these parts of our system publicly for the first time, we want to ensure that users continue to have that great experience, right? That even though they're outside of the context of our dashboards, the users that are like interacting with and building upon these resources feel like really good and have like a happy experience and find that they're guided to the right solution that works for them. So how do we go about doing that? So our dashboard UX has been like polished like really hard over the years. We've tried very hard for many years now, and in the case of both schedules and workflows, we've basically built like full editors, right? So the workflows editor is a large complicated app in and of itself that's buried within our app that allows you to create, preview, test out what a workflow execution would look like. We've built basically an IDE in our web browser for you to like interact with these schedules. And this is also the case for interact with these workflows. And this is also the case for schedules, right? So like we have a schedules editor, which when you're making changes to the schedule, you can get the two like examples of each schedule side by side, and you can sort of eyeball like, oh, does this make sense? Is this person on call at the right time? And you can apply those changes in the future as well. And you can also do this using Terraform if you want to. So you can say, next month we want Liz to join the rotation, for example, or we want to take Rory off the rotation. There's a whole load of like features that we've built in our UI and made sure that they're polished in order to manage what are these really complex resources in an easy way. So like, how do we continue this through into our dashboard? So the first way of doing this is we've built like a very strong building block for doing Terraform generation. So the first entry point I have said here is to make them not do any work at all. So a user can configure a workflow or a schedule in Terraform directly, in our dashboard directly, and we'll give them an escape hatch, right? So either they want to create a new workflow from the in Terraform that matches the specification that they've built in our dashboard, or they want to import a workflow that already existed. And we found that customers wanted to do this when they'd had schedules that workflows that they previously created in the dashboard that they wanted to migrate to manage on Terraform on the release of our Terraform API. And we have like gone really like deep on our Terraform generation in order to make sure that we can fully support these resources being exported in like a really like safe way, right? Like we want to make sure that the guardrails that we have in place for the management of resources in the dashboard also exists when you're interacting it via the API or through Terraform. And then we've also as like large users of Terraforms ourselves, sometimes there are commands which you use in Terraform that you don't use every day, right? I would be lying if I said that I run Terraform import and it runs the first time every time, right? Like managing state in this way is something that some users of Terraform like just don't have to do that often. And when you're importing a workflow from Terraform, we totally agree and support making this as easy as possible. So like we'll write the Terraform command for you and we'll supply you with the correct ID. And here we sort of use the context that our dashboard has of interacting with you as a user and resources that we know about, and we power your infrastructure as code through our dashboard, right? Like they're working in harmony to achieve the goal the user wants, which is to manage these resources in infrastructure as code. And we sort of think that the code you generate is the interface. So like when we've generated these schedules, you can see that we're interleaving things from our dashboard throughout this sort of like creation of this schedule. So if you're importing the schedule and we already know this resource exists, we'll like have a comment that like links you directly to that schedule. We take our API documentation and we place that into the Terraform, right? If you don't want this like commentary, you don't have to have it, but it's very useful sometimes when you're looking at this Terraform, say that you've not used the instant UI that much and you want to understand what these things are, we'll interleave that commentary in the Terraform that we generate, right? So we make this easy for not just a consumer of our dashboard, but a consumer of Terraform that needs some guidance, right? Like every component in our UI that a user is able to edit here would have that sort of description and UX like next to it in the dashboard. So we think it's only right that we also supply that inside of Terraform itself. And the other thing we do is like also as we have a concept of ownership. Terraform generation has been available for applications in a while. Like there's a lot of SaaS apps that support the export of Terraform in order to be able to manage your resources as code. we think that this is like kind of table stakes. If you're releasing Terraform support in 2024, that you need to be able to support that. But what we do to take it one step further is we have the concept of ownership, right? So this is no longer a unidirectional link from the Terraform that we export to our dashboard, but the dashboard is also aware of the context that this has been applied from. Ownership like provides users with a source of truth as to where they're coming from, where this like configuration has come from. So we allow users to set a source URL. This means if I come across a schedule, I am directed to the Git repository where that schedule is created and checked in. And as I make changes to the dashboard, as we use Terraform lifecycle methods in order to claim the ownership of a schedule, right? So this means, or a workflow. So this means we don't allow the editing of the configuration through the dashboard anymore without a user going through an escape hatch. This means that we won't have like state drift occur. Like it won't be the case that someone has edited something in the UI and not reflected those changes in Terraform. We just don't let a user do that in order to avoid that like awkward situation. This also means that but we don't want to make it like difficult for a user to manage these workflows. So to get around that, one thing that we do is we change the save button into an export changes button. So when a user has some configuration that exists in Terraform, that exists in the UI, we'll allow them to export those changes to Terraform, and they can copy and paste them simply from our dashboard into where their infrastructure as code runs. This means that these things are working in consortium, and because we use the lifecycle methods, we know that this has occurred, right? So the user doesn't get into some halfway house state from which they can never recover. Like we understand when when operations have been taken in infrastructure as code and reflect those operations in our dashboard. We're restrictive, so we don't want to allow users to edit the schedule configuration for a schedule that has been managed in Terraform, right? Like a user has made an explicit decision in order to only manage that through infrastructure as code, and that is where the source of truth lies. So for example, we won't let you edit the members of a rotation through the dashboard, but there's some sort of convenience operations that a user might want to take that we do allow to occur in the dashboard, right? An example of this is overrides. We support cover requests in our on-call solution, and it might be the case that I put in a recover request from 5 till 7 because I'm going to the gym or something like that. When a user takes that sort of like cover request operation, we don't block that from happening, right? It's not configuration, it's an action a user wants to take against some configuration that exists. So it's like a happy medium of still having this like dashboard that is like uses the sort of work that we've done in order to make a schedule explicit and usable, but understands like where the source of truth lies here and points users towards it when they want to make changes to that. As part of this, we have built a whole management and management of resource like engine in the back end, right? And this means that these are generalizable. So currently we support this for workflows and schedules, but we have built the sort of building blocks inside of incident.io in order to be able to export this management of resources across the entire application. And that's what we plan to do, right? So like we are going to use the building blocks that we built here in order to be able to export and power this sort of like deeply coupled experience across the entire application stack. And we're really excited to do this. And we think that we've made great choices that makes this a lot more easy to do than something that two sort of components that don't speak to each other. We think it's really, really powerful and allows users of both our dashboard and our infrastructure as code like interfaces to have the best sort of experience that they require. But thanks a lot for your time. I am very, very interested if anyone else is playing with ideas in this space or has any critiques of what we've built here. We think that we've ended on like a really like happy medium and sort of interplay between our dashboard and Terraform. But if there's anything that you think we've missed, any ideas that you've like come across that elevate this any further, like we're really, really interested in hearing those ideas. And I am available on the social media site formerly known as Twitter, now known as X, Rorema with a 0, not a capital O. And I'd really, really welcome any contributions, and so would Incident as a whole. So thanks a lot for your time. I hope that was interesting. Thanks a lot.
Awesome. So thank you for sharing this journey with us, Rory. I absolutely love how you detect which resources are created by Terraform. And I was already thinking of how you guys have built that. But this really makes a good user experience. What are your thoughts, Kareem?
I think for me, this is the exact mindset of content that we want to have at Build. You know, like make people think about like how are you doing stuff with Terraform? How do you make it work for every persona that's represented by your product and that's using your product? So I think, like Rory said, this should be table stakes.
Nice, and that makes a nice bridge to build. So building things for other teams. This is a nice bridge to the next speaker. So our next speaker is going to tell us everything you need to know about like self-service infrastructure and building internal developer platforms. So please give Shaket Joseph a warm welcome.
Hello, everyone, and thank you for joining this session. In this session, I will explain how to implement a self-service culture through proper Terraform management, making it accessible to developers for complete independent work, effectively implementing a significant part of internal developer platform, an IDP. But before we start, let's make a brief introduction. So my name is Shaket Yosef. I've been in the DevOps industry for over 10 years, and I am the founder of Sonora Dev, a platform offering free resources on platform engineering and cloud resources. Additionally, I consult for organizations looking to build an internal developer platform. And before we understand how to build such a platform, let's first understand what an IDP is and why it's important for us. So an IDP is a set of tools and services that enable developers to do anything themselves. And it allows us to eliminate the bottleneck created on DevOps and infrastructure teams, significantly improving the developer productivity, the development experience, and of course, the development speed. And in the diagram here, you can see the flow that I assume most organizations follow. Okay, the development teams request a change in infrastructure or the creation of new infrastructure. The DevOps or SRE edits Terraform code, runs apply, and once everything works, updates the developers that the infrastructure is ready. And here's where the bottleneck occurs, right? There are many developers in the organization, all needing help, not necessarily related to infrastructure updates, right? The DevOps teams have diverse tasks, and their demand is high during the development. So how does the flow look in an organization with an IDP, where developers are completely independent? This is how it looks. Okay, the DevOps team maintains the infrastructure code, but the development teams use and manage it. Okay, for any change, creation, or even deletion, there is no need to wait for infrastructure teams. The developers can do everything by themselves using the code created by the infrastructure teams, of course. But wait, developers usually don't have infrastructure knowledge, which can lead to wasting developer time and even harming productivity. Not to mention the increased risk of human errors, right? So yes, if we don't implement it correctly, it can have the opposite effect. Therefore, I will now present the steps for proper implementation so you can follow the session and do it yourself, provide developers with the infrastructure for independent work, and go to drink your coffee peacefully. So let's go through the steps together. In this step, the first step, we focus on creating our infrastructure as code using building blocks. Okay, think of these blocks like Lego pieces. Each piece is a small reusable module that represents specific part of infrastructure, such as VPC, subnet, or EC2 instance. By using modular components, we ensure that our infrastructure is both reusable and maintainable. This approach allows us to piece together these blocks to form larger and more complex systems with ease. And to make our building blocks even more powerful, we use variables. Variables allows us to parameterize our modules, making them flexible and adaptable to different use cases. Okay, for example, instead of hard coding a specific instance type or region, we use variables to pass these values into the modules. This way, the same module can be used across different environments and projects with minimal change. Organizing our infrastructure into layers. This is crucial for managing states, policies, permissions effectively. And by dividing our infrastructure into layers such as this slide, okay, networking, compute, storage, shared resources, and so on, we can apply different management strategies to each layer. This separation also helps in maintaining clear boundaries and responsibilities, making it easier to manage and troubleshoot our infrastructure. Workspaces in Terraform provide an isolated environment for different stages of our infrastructure, such as development, testing, staging, and production, so on. These isolations allow the developer to create, test, and destroy environments without affecting others. Using the workspaces when infrastructure is written in a generic and modular way, it allows developers to create a new workspace based on the same code and use it as personal environment or feature environment that can be removed when no longer needed, for example, by pull request events, and all while ensuring our stable environments are not affected by ongoing testing or development. Pre-built templates are a great way to speed up the deployment process or service creation process, which is great and important in microservice architectures. And these templates serve as blueprints for common infrastructure patterns and configurations. And by providing the templates, we reduce the time and the effort required to set up a new environment or service, ensuring consistency and best practices across organizations, which is very important in the self-service culture. And in self-service culture, collaboration is key in any infrastructure project. So using deployment tools like Terraform Cloud or other CI/CD platforms helps streamline the teamwork and manage the deployments more effectively. Okay, I love Env0 and Torque as well, so I added these tools to this slide. And these tools provide features like drift detection, policies, and automated workflow, and making it easier for teams to collaborate and deploy infrastructure safely and efficiently. And last but not least, before we giving the developers the capability to make anything they want, it's crucial to ensure they have the necessary knowledge and training, okay? They don't need to be DevOps or SRE expert, right? But they should understand the implications of their actions. So providing training sessions, internal workshops, and documentation helps equip developers with the skills they need to manage the infrastructure safely and effectively. Let's demo it. Okay, so here we see a basic diagram of two templates, one for an ECS application and one for a serverless application. Each template contains blocks associated with specific layers: shared, app, and network. The app layer is the one I will be making available to developers as a self-serve option. This layer will contain application resources that developers can edit, add to, or remove from. All the workspaces in this layer will have access to the information exposed by the other layers, shared and network, actually the outputs of the states. But any changes made in the app workspaces will not affect the shared and the network layers. We will also restrict developers from making changes to the states of those layers, the shared and the network. Okay, so here is a basic example of an ECS template I created. In the root directory, we have the Docker file, the README, and the application's requirements. In the source folder, you will find the Python code, where I created a very basic Hello World application. And the demo focus is on the last directory, the infrastructure. Inside this directory, you will find 3 subdirectories, each representing a layer. The shared and the network layers contain resources that are common to all the app environments, the app workspaces actually. But only DevOps and infrastructure personnel have permissions to make change there. For instance, I've placed the ECR repository in the shared layer, which will store the images for all the environments. These images will be uploaded by the CI/CD pipeline, which I also created as part of the shared layer. In the network layer, you will find the VPC, NAT gateway, and any other resources related to the communication of our services. In these 2 layers, we will not create a workspace per environment, okay? Instead, we will have a single workspace or 2, for example, non-prod and prod. And in the app layer, we will place all the resources related to our application. Here, for instance, I've only included the ECS cluster, but if we need a database that should exist in every environment, in every app workspace, we will create in the app layer as well. And now we can define this project as a template. The simplest way to make templates accessible is through GitHub. This is especially useful for those who don't use the developer portal or any other self-service tool. By checking a checkbox in the repository settings, you can mark the repository as a template. This way, when creating a new repository, developers can choose to use the template. And of course, if we want to enhance the process, we can add cookie cutter and automation that runs immediately after the repository is created, using GitHub Actions, for example. Alternatively, we could even run the entire process through developer portal or the infrastructure deployment tool you are using. As I mentioned earlier, collaboration is crucial when working with infrastructures. Therefore, any change, creation, or deletions of app workspaces, as well as shared and network workspaces, should be done through the infrastructure deployment tool adopted by your organization. If you don't have one yet, talk to me after the session and I will send you recommendations and reviews based on the extensive research I've conducted. And that's it. Thank you for listening. You can scan the code and watch free resources that I publish every week. And of course, feel free to ask questions if you have in the chat. Bye-bye.
Nice. Thank you very much, Shiket. So making sure that engineers can work autonomously is key. It reduces time to value, minimizes friction, and ensures a consistent user experience for your internal end users. Optimize for joy and minimize waste. Now, you've probably seen that Kareem is not in the stream. His vault token expired, and we are working very hard with the producers to get a new vault token for him. So you gotta bear with me for a moment. But we've recently announced general availability of the AWS CC Terraform provider, a provider that's completely auto-generated through the AWS Cloud Control API. How awesome is that, right? So sometimes the AWS Terraform provider lacks support for a service due to its handwritten nature and how we prioritize support through community upvotes on GitHub. Now, the AWS CC provider may already support that service that's lacking support in the other AWS provider due to it being auto-generated. This way, you can actually use both AWS providers, where the AWS CC provider is complementing the standard AWS provider. Now, Glenn Kia, one of AWS's contributors to the AWS Terraform providers, is going to tell us all about using the AWS and the AWS CC providers and how you could possibly migrate state between one another without recreating things. Chat, please give a warm welcome for Glenn.
Hello everyone, thank you for joining us today for HashiTalks build. Today, we will be talking about migrating Terraform state between providers, specifically migrating between the AWS and AWS SEC providers while preserving resources. I'm Glenn, a cloud architect at AWS. I've been using both providers in several projects, and I'll share some lessons learned during the implementation. So let's get started. This is what we will cover today. I'll share some background on the AWS SEC provider and briefly highlight some scenarios for using the AWS SEC and AWS providers together. We'll then dive into the crux of today's talk, which is to show how to migrate state between providers, starting with simple resources before discussing the approach when it comes to resources within modules. I'll highlight some edge cases when migrating as well. Finally, I'll show two ways that we can generate AWS SEC or AWS provider code given the other. Let's start with some background on the AWS SEC provider. The AWS SEC provider was GA'd on 30th May 2024, and it's built around the Cloud Control API. An interesting fact about the provider is that it is automatically generated based on the Cloud Control API published by AWS. This means that it can potentially support new resources if there is resource support in Cloud Control, among other conditions. Do check out this blog that elaborates on the GA release. So when will we find ourselves using both providers together? A common use case is to have complementary coverage between providers. On the left, you'll see a screenshot of the AWS provider, and on the right, you'll see a screenshot of the AWS SEC provider. Perhaps you are looking for a resource that can accept transit gateway attachments. In this case, you would choose the transit gateway VPC attachment acceptor from the AWS provider. On the other hand, if you're looking for a resource to create AWS backup restore testing plans, you will opt for the backup restore testing plan resource from the AWS SEC provider on the right. This can complement existing AWS backup resources that you may have deployed using the AWS provider on the left. To help get started on how you can use the two providers together, a few of us have published a workshop with step-by-step instructions on how to achieve it. In this workshop, we also talk about using provider aliasing for multi-region deployments and how we can use an open source module to account for tag differences between the providers. So this is the link to the workshop over here. Now, after using the AWS SEC or AWS provider, you might have a use case of consolidating state into a single provider. Some possible reasons for doing so are as follows. Perhaps the rationale for using the AWS SEC provider is to deploy resources not yet supported by the AWS provider. This could be because the AWS SEC provider is automatically generated based on Cloud Control API resource support, whereas the AWS provider requires developers and engineers to code out resources by referencing their API schemas. Another reason could be to reduce the efforts needed to keep up with two changelogs if you're using two providers. When we move to a single provider, we just have to keep up to date with one of the changelogs. Third, you might be considering reducing the total number of dependencies required by your infrastructure as code. When you consolidate state to one provider, a Terraform init will now download only one of the providers instead of both of them, reducing the size of your downloads. This is not an exhaustive list, and perhaps you will have other reasons for consolidating state, and we would love to hear them as well. So in our first example, let's see how we can migrate state from the AWS SEC to AWS provider using CLI commands. For all examples in this talk, it is recommended to test this in a dev environment with resources that can potentially be unexpectedly destroyed, and also to keep a backup of the state file. In addition, make sure to review the output of Terraform plan commands before making any changes. So for this demo, we'll first create a VPC and subnet. We'll create an AWS SEC EC2 VPC, and we'll reference it in an AWS subnet resource, as you can see over here. So running Terraform apply will create the base resource. Next, we review the documentation for the AWS provider VPC resource and see that it uses the VPC ID for imports. We then review the documentation for both providers and understand the arguments that both expect. In this case, it's convenient because both arguments are identical, which is the CIDR block argument. With that, we can refactor the code by replacing AWS SEC EC2 VPC to AWS VPC. It will look like the following. Now we are using AWS VPC and referencing it in AWS subnet. The CIDR block argument remains the same for both AWS and AWS SEC resources. Now we're going to run import commands to import AWS VPC resource into state. We first extract the VPC ID from the AWS SEC resource using Terraform state show, as you can see over here. An alternative is to grab it from the console or use AWS describe VPC's API call. Now with the VPC ID, we can then use it in a Terraform import call, as you can see over here. So this is the example of a multi-line command. If you want to do it in a single command, this is an example provided in the screenshot over here. Next, we can remove the AWS SEC EC2 VPC resource from the code. The code now only uses the AWS provider resource. Finally, we remove the AWS SEC VPC resource from state. We will run Terraform state remove and specify the AWS SEC EC2 VPC resource over here. And the output of the command when successfully run is shown here. Now to be safe, let's run a Terraform plan to make sure that there are only AWS resources in state and that there are no unexpected drifts. So we can see our AWS provider VPC and AWS provider subnet in state, and there are no changes to our infrastructure. If you're looking to use your existing pipelines to Terraform applied, you can consider using import and remove blocks. Let's see how that works, this time using AWS to AWS SEC provider migration. So we first create an AWS VPC, this using the AWS provider, and reference it in AWS SEC EC2 subnet. We run Terraform apply to create our base infrastructure. Let's take note of the VPC ID over here, as this is used in a subsequent step. Next, similar to the previous example, let's take a look at the documentation that describes the import requirements for AWS SEC VPC. The documentation mentions that it uses the resource ID. The ID of a resource is generally defined by its equivalent CloudFormation resource ID. Taking a look at the CloudFormation documentation shows that the resource ID references the VPC ID, as you can see over here. The links to both the Terraform and CloudFormation documentation are shown here. Note that there are some nuances to the IDs used by AWS SEC resources. Please reference the following two links that explain it in greater detail. Once you have understood the AWS SEC resource import requirements, let's declare an import block to import the existing VPC, which is the AWS SEC provider VPC, into state. Next, let's run the Terraform plan generate config out command. So unlike the previous example where we hand-coded the new resource, in this example, we'll use this command to automatically generate a resource configuration from the VPC ID supplied. We run this command, and some details about the fields it discovered are shown when the command is run, as you can see over here. The command reads details about the VPC and creates the Terraform configuration in a file called generated.tf. So this is a link on how this particular command works. So the contents of the generated file is shown in this screenshot, where the details are simpler compared to the output of the Terraform plan command earlier. The command makes a best guess at the appropriate values for each resource argument. As we can see here, there are extra arguments that are not needed. Hence, we will just use the cider block argument. Now let's introduce that resource here and also modify AWS SEC subnet to point to the AWS SEC VPC. We also introduce the remove block to remove the AWS provider VPC. In this remove block, we define a lifecycle with destroy equals false to preserve the VPC resource in the AWS account. We then add an import block to import the AWS SEC VPC into state. Running a Terraform plan apply shows that the AWS provider VPC resource will no longer be managed by Terraform, but will also not be destroyed. The command also shows that the AWS SEC VPC resource will be imported. In summary, we will just have one imported resource with no resources being destroyed or updated. As a way to clean up the helper blocks that have been used, we can delete the removed and import blocks from our Terraform configuration. And as usual, we can do an additional Terraform plan to make sure that there are no unexpected drifts. With that, we are done. Now, some might be wondering, why didn't we do a Terraform state move? Well, while the resources are fundamentally the same, in this case, a VPC, they are still viewed as different resource types. Running a Terraform state move command results in an error that the resource types don't match. In the screenshot below, we can run state move commands when the resource types match. For example, an AWS provider VPC named this to another AWS provider VPC named destination, and the command succeeds. Now that we've covered the basics of moving state between resources from different providers, let's see how we can handle the same, but this time, resources between providers that are within a module. Let's start with the following folder structure. Here we have a main.tf file that initializes our module named network. Within network, we define an AWS SCC provider VPC. Running an apply shows that we have added a VPC within the module. The next step is similar to the ones we have done previously. Inside the module's main.tf, we switch the AWS SCC provider VPC resource to the AWS provider VPC resource. In our root main.tf file, we introduce the remove block that removes the module's AWS SCC provider VPC resource, and an import block that imports the AWS provider resource within the module. So these blocks are defined over here. Running a Terraform apply shows that the AWS VPC will be imported, and the AWS SCC VPC will no longer be managed by Terraform, but will not be destroyed. Overall, there's just one resource to be imported, and we expect no changes in our infrastructure. Again, once we are done, we can remove the removed and import blocks and run another plan to validate that there are no drifts or changes to the infrastructure. One gotcha to note is that the import block must be added to the root main.tf file. Adding the import block into the module's main.tf file will result in an error that import blocks are only allowed in the root module. This is shown in the screenshot over here. So if you add the import block within the module, it results in the error over here. So far, we've been importing very simple VPCs with a single argument. In reality, there are resources with more complex argument types and dependencies. This talk will not cover all the different cases, but we'll cover two of them. So the first example is import values that differ between providers. So let's use the AWS SCC VPC lattice service as an example. We first initialize the resource, and then we Terraform apply it. Running Terraform state shows that the ID is mapped to the ARN of the resource, while there's another ID mapped to service ID. These two values are different. Now, when we look at the AWS provider VPC lattice service, we see that it uses the service ID as its ID for imports. It does not use the ARN. So this is the service ID of the resource. Hence, when you run the import command, instead of reading the ID attribute of the AWS SCC VPC lattice service, we'll instead read the service underscore ID argument over here. This is the value that starts with SVC hyphen, as you can see here. Doing so results in the successful import of the AWS provider VPC lattice resource. Another potential gotcha when migrating between providers is that the names given to arguments could differ. In this example, we see that the AWS provider S3 bucket sets the bucket name using an argument called bucket. On the other hand, the AWS SCC provider S3 bucket sets the bucket name using the bucket underscore name argument. Hence, when we refactor code to a new provider, we must also account for these differences. This is different from the first VPC resource example, where both use the same argument of cider underscore block. So let's see that in action. First, we create an AWS SCC S3 bucket. We then prepare our code for migration by declaring the remove blocks, import blocks, and the S3 bucket using the AWS provider. Notice here that the bucket name is specified using the bucket argument. Also notice that the text used in the AWS provider resource differs slightly from the AWS SCC provider resource. So these are our remove blocks, our import blocks, and our new AWS provider S3 bucket resource. we run a Terraform apply. This time, in addition to the AWS provider S3 bucket being imported, we also see that there are some arguments that will be updated. This includes the force destroy, which is an AWS provider specific argument that defaults to false, and that the tags would be remapped. The changes look good, and we can proceed. So finally, as usual, we run a plan to make sure that there are no infrastructure changes or drifts post-migration. And now we see AWS S3 bucket within our state. In the next part, I will show various automated approaches to convert code between providers. This gives an alternative approach to reading the documentation of both providers and converting code by hand. The first that we've seen earlier is using Terraform config generation. It generates code for resources based on the ID specified in import blocks. This is available in Terraform v1.5 as an experimental feature. Terraform generates the HCL based on its best guesses for appropriate values for each resource argument. Just run the following command: terraform plan -generate -config-out equals generated resources.tf, as we have done previously. Let's quickly recap how this is done using the S3 bucket resource. So we first create our AWS SEC provider S3 bucket. And then now we declare our import block for AWS provider S3 bucket. In this case, the ID is the bucket name. We then run terraform plan generate config command, specifying the output file as generated resources.tf. Running this command shows how Terraform guesses the values of the attributes of the bucket. You can see some attributes being guessed in the output over here. Now let's view the contents of generated resources.tf. In this file, we see that Terraform accurately mapped the bucket's name to the bucket argument of the AWS provider S3 bucket resource. We also see that there are several extra arguments defined that we do not need. These are highlighted in the screenshot and we can ignore them. We can then proceed to do our migration like what we have done in the previous section for S3 buckets. Another approach to automatically generate Terraform configurations is to use generative AI. For this example, let's use a more complex resource like the AWS provider backup plan resource. We see that we have more complex arguments and even nested arguments like lifecycle and backup options. Using the sample prompt above, in the middle of the screen, we enter the code for the AWS provider backup plan over here. We also enter the documentation for the AWS provider resource for backup plans and the documentation for the AWS SEC provider resource for backup plans. The documentation for these are available at the link supplied. Note that this is just a sample prompt and you might have to tweak the prompt to fit your needs. For this demo, I use Entropic's Claude 3 Sonnet, which is available on Amazon Bedrock. The result is shown in the screenshot. So we can see the AWS SEC backup plan resource generated with all the arguments that it requires. So let's see it in action. First, we create the AWS provider backup plan resource. This is the same Terraform configuration block that was originally passed to the large language model. We can see that both the backup vault and the backup plan have been created. We then prepare the code for migration. We add an import block for the AWS SEC provider's backup plan resource. We add a remove block to remove the AWS provider backup plan resource from state. Remember that we add destroy equals false in the lifecycle block. Finally, we declare the AWS SEC provider's backup plan resource that was the output of the large language model. This was copy and pasted from the LLM. Running Terraform plan results in the following. We can see that the import of the AWS SEC provider backup plan is successful, and that the state for the AWS provider's backup plan is removed, but the resource will not be destroyed over here. We can then delete the import and removed blocks after the migration is complete. And finally, we can run another Terraform plan to validate that there are no drifts or unexpected changes. In this talk, we covered various strategies for migrating state between Terraform providers. This involves migrating state between resources at the top level main.tf and resources within modules. We went through a few potential edge cases that you may encounter and how to address them. Finally, we explored how we can use Terraform's config generation to automatically generate HCL, and also how we can leverage large language models to do code conversion between providers. Thank you for tuning into this talk, and I'd love to hear about your experience migrating Terraform state. Thank you.
Thank you, Glenn. This was so helpful. So even though I work a lot with the AWS provider myself, I was not aware on how to do this. So having the ability to use new resources from the AWS CC provider and migrating them over once support is there on the AWS provider is great. I love it. Now, monorepo or not? Opinions differ. Is it all the infrastructure code in your entire organization? Or is it per domain or per team? And what makes a monorepo a monorepo? And what are your thoughts about a Terraform monorepo? Let us know in the chat, please. Our next speaker, Dimitro, knows all about monorepos, and especially on how to survive a monorepo mess. So let's see what they have to share with us on monorepos. Please give Dimitro a warm welcome.
Hello everyone, and welcome to my talk, Multiple Terraform Projects in a Monorepo, How to Survive a Mess. My name is Dmitro Prekrasny, I am a Principal DevOps Engineer at Westwing. I like everything that related to DevOps and coding. I'm trying to automate everything. I'm a fan of clean code, infrastructure as a code, and open source. I used to be also a software engineer, and here you can find my LinkedIn profile if you would like to contact me. And without further ado, let's go. So it's quite often happening that DevOps engineers or DevOps teams need to support several dev teams, which also has multiple applications or microservices under their area. And it's quite often that, yes, you have infrastructure as a code, but it organized in a way that it's hard to maintain it or hard to handle that. And today we will talk about that. So what is the agenda for today? We will talk about prerequisites, what we have at the beginning. We will then have a problem deep dive. We will explore existing solutions. We will introduce Terraform Compose. That's a small tool that I wrote to help me with managing that. I will do a quick demo and a couple final words in the end. So, as a prerequisite, we have a set of projects in a monorepo, because you can have a project in a separate repo, but in case if you support multiple teams at the time and each team has multiple applications or microservices, it's quite often that it's more useful to organize it in a way that multiple projects that belongs to the same dev team sits in a monorepo. And then we face this situation that, okay, every project might have different project structure, it might have different Terraform versions, it might have various workspaces, which we quite often use as environments. And with that, so what we understand on the multiple projects. So we might have different projects like alerts, a CMS, portal, whatever. Beside that, we might have shared modules or shared Terraform code, which is common for all of that projects. Projects also might be organized in a separate environments Terraform code folders, or it also might have a various versions, which we will see further. Various workspaces. So every project might have different set of workspaces, and that will do almost impossible to reusing any snippets or any scripts across them, because if you have different set of the workspaces, how you will manage that? It might also have different structures. For example, some of the projects might have a sub-components, like, for example, we see our vouchers project, which has app and platform components inside. And that also complicates snippets, working snippets or scripts for your automation. And as I mentioned, it might have different Terraform versions across the projects or even across the different workspaces at the same project, because you might be in the process of upgrading your Terraform version. So what does it mean for us? Well, we have a problem when we switch in Terraform versions on our local. For example, you want to switch your staging to the new Terraform version, but you want to keep your production on the old version for some time to test it. Then it's quite hard to achieve that when you especially need to support both versions for some time. Also, there is a risk of incompatibility of the snippets, and when you have a different subfolder structure or workspaces, it's unable to use unified snippets. When we talk about workspaces, it's also, so there are also no visualization of it, and it's not trackable by version control system, so it's bad for audit purposes, for example, and it's hard to onboard your colleagues, newcomers, or it's hard to troubleshoot because you need to memorize every single project, every single workspace to know what is running where. Aren't there any solutions? Well, let's check. So actually, we have 4 potential solutions for that. This is Terraform Cloud, which is SaaS solution native to the Terraform itself. This is TerraGrant, which is also a famous solution for that, and TerraMate and TerraSpace. And the better choice for that would be probably TerraGrant, but it has also a couple not solved problems. For example, here you still need to take care about switching Terraform versions on your local machine. That's actually a pain point which is no one of them can help you with. But beside that, also you need to still remember the structure of your projects, the workspace list, etc. And yeah, you need to create quite a lot of files, sidecar files, sitting in a different folders, which will describe for the Terra grant the structure of your project and help integrate your project with Terra grant. It's not super complex, and it's famous solution. So you can Google that in Stack Overflow, for example, but it's not. You still need to maintain that, and it's not that fast as I wanted. And beside that, as I mentioned, you still need to take care about switching Terraform versions for your local machine. And same for Terraform Cloud. This is SaaS solution. This is good, but it's also pricey actually. And you still need to take care about switching Terraform projects on your local machine, unless you do everything in Terraform Cloud, using their runners, using everything there. But then you need to also remember what Terraform version were and what workspace were, because it's still not solved. Okay, so don't we have any similar solutions? Yes, we have. And we have them in Docker Compose. Docker Compose plays the same role as organizer for the Docker images. And I thought that, okay, we might have something for the Terraform as well. And that's why actually the idea of terra-compose comes to my mind. So I was supposed to reuse the same approach, config as a code, high visibility and traceability and so on, and build that on top of the flexibility of the Docker. Makes me able to play with different Terraform versions at the same time. Let's make a quick wrapper on top of it. So on this collaboration diagram, you might see how terra-compose collaborate with Terraform. Using the config file, where you can define path to your project, workspace, Terraform version, and so on. Under the hood, it will run Docker with the proper Terraform Docker image, spin up a Docker container, and run a set of Terraform commands inside. It also allows us to attach different activities and chain actually Terraform commands to reduce the number of commands that you need to type, and for such actions, for such common actions like build a plan or apply. For example, we can select workspace up front because we know what workspace we want to use based on the config file. We might also run Terraform init, Terraform validation, etc. before building a plan, so you can avoid pops up errors in the future early, and then you can apply a Terraform actions, and even we can run some cleanup scripts afterwards. So in this way we will solve Terraform version update thanks to the Docker engine underline. We also don't care anymore about various workspaces And we don't need to memorize all of them because we have this config file which describes everything. The only thing that we still need to do is to actually build this config file, but this is one-time actions. It's very quick, and the benefit is much more than effort that you will spend on it. And you also can chain Terraform commands, as I mentioned before. That will speed up the development process, and it will shift left your errors, which might pops up later on your CI. And as I mentioned also before, we might have a post actions like cleanup. So as a benefit that we have, project attributes as a code, so you don't need to remember means less errors. It has the same visibility as a code base, which is very good for audit purposes, for example, and for keeping your code, keeping your infrastructure in the code and reduce the number of drifts. And also, you have a guaranteed validated plan thanks to this chaining Terraform commands. It also speed up a maintenance and shift left your errors. Less time for double check, less time for printing repeated commands, and less validation failures. Use cases for terra-compose is most are following. This is plan and apply, as I mentioned. And under the hood, for the plan, it will run Terraform init, Terraform select workspace, Terraform format check, validation, and plan. For apply, it will also run init, select workspace, check for approve, apply, and clean up. It also might be useful to just list available workspaces to run any custom command inside and run and just jump in the shell, and you can run one or several commands inside. You can do whatever you want because you in the shell inside the container. Here you can see example of the output of the help command of the terra-compose, and this is example of the config file. Here we have a default section which is default for all projects, and we have aliases for every project and environment. So we actually have items here, a pair, project, environment. We will see that later. This is the main sections in the config file. And we can define Terraform version in default, for example, section, and we might want to overwrite it in particular project, and it's possible. Only one property is required is path, because terra-compose needs to know where exactly your project is located. And here we can also see example of using hooks. In this case, this is before Terraform init. We want to run. We want to remove .terraform folder to, for example, run a custom backend config for customize our Terraform state location, for example. Okay, so now it's time for a short demo. Okay, let's start with our demo. and I will show you a few use cases for that tool. So first, I want to give you an example how we can deal with nested project structure with optional backend config and hooks and shell action. So we will use app component of the portal project for the demo. And here you can see the structure of the app component. So we have projects folder, we have portal application, and we have app component of it. Inside we have few Terraform files. We keep our state inside the folder. This is for sure for demo purposes only. And we have here the main folder with the state. And for example, you want to do some experiment. And for that, you check out your state to another folder. In this case, experiment folder. For integration only. So if we check our config, we can see that we have two definitions here. We have for one definition for integration environment, where we defined our path, our workspace, backend config. This is customization that I've just told about, and a hook. So this hook we will see later how it can help us, and also another one for the live project. So let's run plan action and see what happens. So now you see we are running webhook before Terraform init, which we define it here, and it tells us where exactly we are, what folder we are working on, with what options our Terraform init runs, and so on. So like it gives you details what happens there behind the skins. This is standard output of the Terraform plan, Terraform init, and so on. So you can see what happens there, and also you can see here that okay, we currently found workspace integration in config. We select init, we check format and validate Terraform templates, etc. So you can see the whole flow, what happens there. Then it gives you details about with what parameters Terraform plan has been built, and it also says that yeah, we did not define Terraform vars file name at the config, but actually we have Terraform vars file with the same name as our workspace, and we are gonna use it as a Terraform vars file. So this is basically the default behavior. Now we built the plan and saved it in the plan tf plan file. Now let's try to apply action, and now we can, this is optionally, but we can use also suffix with the plan and apply. We can use suffix debug to skip init process and validation process. This is useful for development because you don't need to reinitiate Terraform project when you do some development process, and with back and forth activity you don't need to wait more, so you can skip it for that. But for the normal plan and apply, it's always better to have validation in the process. So that's kind of option to speed up the development process. And it also gives you some information about workspace where it's running and workspace selected. Also ask for approving to proceed with apply of the plan. And it also, so the apply based on the belt that we, based on the plan that we built before. So we this is kind of guarantee that we will not include some changes that might pops up recently. But it also protect you with information that this plan actually was modified how many time ago, because this protect you from situation when you build this plan file and then you apply this file in several hours, and this is maybe already a stale file, so it kind of also protect you from this side as well. So let's proceed. Yeah, we created some resources there. We have a security group, and here we can see that our changes actually were applied to the experiment one, not the main Terraform state, but with experiment one, because you see the backup has been created. And so that means that our backend config actually works. And let's check that we have one more security group. Yes, we have it. Now, if we check how our shell option works, we can run it. So yeah, we have our structure of our .terraform like that, and we can actually shell into container and check what that it actually works. So for that, it's very simple action. It's just a shell command, and it gives you information that you are shelling into this project, and it's also ask you for approve, because you need to be careful there, right? So you can do quite dangerous things. And you there, like not very sophisticated. You can check that we have, for example, you can run for workspace list there, for example, and we have default and integration. You remember that we were actually on the our experiment branch, let's say, of the state. And now if you want to run same plan for live environment, you will encounter error, because like without these hooks you will encounter the error, because we need to switch our local pointer to another state folder, and for that we have this Terraform init webhook, which will just remove our information about pointer and we'll run Terraform init from the scratch. So this webhook in this situation just help us to have different state locations, and it's transparent for the end user. And you see that the plan actually has been built. We have this Terraform plan for this workspace without any errors, without anything. It's just you just can apply it as well. It also will transparent for the end user. And you see that, yeah, it works. And let's check that we have this security group created. It is. We have second security group created. Okay, that's it for the demo that I wanted to show you. Let's switch back to the presentation. Good. So now let's check. Is everything already done or not? Let's check our pain points that we defined before. We solved a problem with switching Terraform versions on local environment. Now it's just an attribute in YAML. We solved our snippets incompatibility. Well, it's partially solved. Why partially? Because you still need to think how to allow your snippets being run, because you need to run them inside the container. So you need to place them in a way that it will be available inside the container. But yeah, it's beside that, it already universally works. We solved the problem with visualization of the current workspace. You saw in the command line output that we clearly see in which workspace we are. It's much easier now to onboard newcomers, and now it's trackable by version control system if you include for sure this config in the version control system, which I would recommend to do. Which is still partially solved is automate routines and chaining commands. So chain commands we have, but it's not customizable at the moment, and this is actually that I will talk about it later. This is part of the future plans. Then we also solved, we don't need to remember anymore our structure, our workspace or version, and about the complexity and time to implement. So this is very simple YAML, you saw, and for integrate a new project to use terra-compose, for me it took so I did that several times, and for me it took like maximum 1 hour, and it's open source, so it's free. Okay, what about future? Because it was a quick wrapper 3 years ago, so it was not the command interface was not proper designed, I'd say, and I thought about improving that. Beside that, I also mentioned I wanted to make actions customizable and let you also customize the chain of the commands that you are running. Well, and if I would have time, I would also rewrite it in Go, because at the moment this is a bash script. And here you can find a link to GitHub account with terra-compose. Please, I want to encourage you to also contribute to this tool if you are interested in. If you have any questions, please contact me via GitHub or via LinkedIn. And with that, I want to say thank you for your attention. Have a nice day and have a fun.
Thanks for this talk, Dimitro. It's nice to see what you've done with terra-compose. Actually, we've been recently working on Terraform Stacks, which is a new feature to simplify infrastructure provisioning and management at scale. I'll make sure to share a link in the chat as well if you want to learn more about that. And it should solve similar challenges one might face in a monorepo, as well as rolling out against different accounts and regions. So stay tuned for that. Very nice talk. Thank you, Dimitro. Now, on another note, HashiConf registration is live. So join us in October 14 until 16 in Boston. HashiConf brings together developers, IT leaders, industry partners, and others in the HashiCorp community to talk about infrastructure and security lifecycle management. There will be technical talks, strategy sessions, and social events. For more information, visit hashiconf.com. I will make sure to share a link as well, and I'll see you there. Now, let's take it one step further in that structuring and organizing journey of your code, resources, and even your platform. How do you structure your HTTP Terraform organization, and how do you monitor what you roll out? Our next speaker is going to tell you everything you need to know about this. Chat, please give a warm welcome to François Dessemblin.
Hello everyone and welcome to this session. This session will talk about the CSO organization-wide observability with HCP Terraform and AWS CloudWatch. We will see first what is exactly the problem and what I come to build this solution. Just a quick reminder just after is what is CloudWatch OIM and how it works if you don't know it. And we will talk about our target architecture that I will show you how it works, and just after we'll go in the code directly and we'll see how we can implement this solution with HTTP Terraform and our AWS accounts. Just before beginning, I will just introduce myself. So I'm François D'Exemple. I am a cloud engineer at Devoteam Cloud. Devoteam Cloud is a consulting firm based in Paris, but we work across all the Europe. And also I am an HashiCorp ambassador. So, what is exactly the problem? That's the Live My Life of an answer. When I go to my different clients, I see that they have implemented the AWS best practice. So this is just one screenshot with an example with 5 accounts, but in general, when I go to their account, to their organization, we talk about hundreds of accounts because, or even thousands sometimes, because they create one account by project, and that's fine. But even I see one client that was creating one account per microservices or something like that. So it's really fine. But when in the morning I go to my computer, I want to see the metric, or if I have a bug, and I want to see what is not working, and to see in different multiple accounts. When I log into one, I see my dashboard, and I open a new tab with a new account, and what happens? And I'm disconnected from the first one. So I can't compare the metrics and see multiple metrics across the different accounts, and that's a problem. And that's really annoying in my job. So that's why I need to find a solution on how I can see all the metrics of all the accounts in the same CloudWatch dashboard. And okay, there is some solutions that sometimes we don't need that because they have some tools like Datadog, Dynatrace, so we can plug all the data into this unique tool, so I can see all the accounts in the same place, but I want to keep it fast just on AWS. So, what is CloudWatch Observability Access Manager and how it's working? So this is really simple. This is a schematic take from the AWS documentation. So we'll have one central monitoring account that you can see on the schema, and on this, each tenant account or organization account, we create a link to this central monitoring account, and this central monitoring account have a sync when the tenant account will send their data. And that's how we can have the cross-account observability. Just a quick reminder, when I talk about observability, what is observability? In observability, we have three main things: the metrics, the logs, and the trace. These three things are the pillars of the observability in general for all platforms. But also, with CloudWatch, we have two other things. We have the application insights that we can send to the CloudWatch Authority Manager, and we have the internet monitors. That's two things that we can send. So what you can share between your tenant account to the observability account is the metrics, the log, the trace, the application insight, and the internet monitors. Okay. Now, let's discuss about our target architecture. First, so here I will assume that you have nothing. You just create one account on AWS, you have activate AWS organization, and that's all. You did nothing on all your architecture. So I will manage this AWS organization management account with HTTP Terraform on the Cloud Edition. Typically, I will push my code on GitHub, all my Terraform code. This I will implement just a little GitHub action because I want to manage some rules before on GitHub. So that's GitHub that will trigger the apply on Terraform, the plan on the apply on Terraform Cloud. Also, that's the goal. We will create some fake project accounts. So just for the example, we'll create 3 projects. Each account will be managed by a dedicated Terraform Cloud workspace. So workspace, this is not a workspace like maybe some people can say, okay, I know workspace with Terraform, the community edition, but that's not the same thing. The workspace is more like a dedicated project inside Terraform Cloud. So in Terraform Cloud you have project, under you have some workspace, and your workspace is your Terraform stack. I will not create this Terraform workspace manually, so this is my first tag, the organization management account, that will automatically create the Terraform Cloud workspace when I want to create a new account. This new account, this new workspace will be linked to a GitHub dedicated account, a dedicated repository repository. So I will have the same repository for each account because this will like a kind like a landing zone. So we will use the same base, and this Terraform code that will be triggered by that will read GitHub, and that will trigger automatically. There is no GitHub action on this part. And after, the Terraform Cloud will apply directly on the AWS account. And of course, the Terraform will create an account dedicated to the observability. In this case, we will not create a dedicated workspace because this is kind of special, and I will keep it under the management of the workspace that has the organization management account. So, yeah, that we have. And you can see here the arrow that our Terraform Cloud will deploy some resource on this account, because if we deploy it all automatically, our Terraform can have the right to create and modify resources. So we have many choice. One of the solutions that I selected was CloudFormation stack set, because that will be the simple and the stack will keep pretty simple. We just create one IAM role on each account that will allow Terraform to assume the role and to create the resource after on the account. So in the definition of this CloudFormation, that's just one IAM role that will be the same for the Terraform, and that's all. So Terraform after will assume the role. Will have, so after with the key that's just get by AWS STs, we create or modify the resource or even destroy it. That's it. And after that, on each account, we create our Observability Account Manager, the link in the region with list 1, and also we create the REM sync for the account observability. And yeah, just I think you notice it when we create a link or a sync, it's dedicated to AWS region. So in my case, I work in every time in the West 1 because I have some resources like cloud funds that are running it, but all the others are in Paris region, so the West 3, so I need to create another link. Okay, now we'll see how we can implement this. So, as I was explaining just before, we have two repository GitHub. We have the AWS org that will contain all of our Terraform code for AWS organization, but also the observability account. And also we have another repository GitHub, so that's for the shield accounts that will contain like our landing zone. Here we just have the CloudWatch link, but if you want later to create some roles, some I don't know, whatever, you can do it in this text, and it will be created like general rules for all accounts. So first, we need to do some manual job, because I told you, we just write our AWS organization and we cannot link Terraform and AWS like that, and it's not automatically for the first time. We'll see that for the shield accounts we'll create a stack set, but that will create a role, but here we need to create a role manually. The first thing, we need to create an identity provider in the master account. So you go on IAM, identity provider, create a new identity provider, and we'll select an OpenID connect, and we have two parameters to put. The first one is the provider URL. This is the URL of the tenant on Terraform or UI. Generally it will be app.terraform.io, but maybe we change with HTTP, and if you're on the HTTP US or HTTP Europe, it will be not the same, I think, provider URL. And the audience, the aws.workload.identity. This is something like static, it's right on the Terraform documentation. Of course, we are creating an identity provider for what? For creating a role just after the role, because I don't want to put my, we can do that, but it's not recommended to put some AWS access key and AWS secret key in the environment variable. It will be working, but it's not recommended. So that's why we create a role. Typically, this is the policy of the role that I will create. Just keep it simple here. So we just allow everything on anything, and this is the truth entity that it's just a more complex. So the first thing we will allow just the ODC parameter that we just want to create. So don't forget to change the account ID and your and the name of the provider. And after that's really something that it's really important to be carefully with that. So this is the condition, the action. So we'll just check the audience. So AWS.workload it will not change for you, I think. And after the string light. Why? Because you have to put the organization that your organization Terraform. And if here you just put a star, that means if I want, because I'm the same shared tenant of Terraform, I will be able to deploy some resources on your account. So that's important to put your org, your project, your workspace, or just if you want to create one role for all the project and all the workspace, you can do stuff, but never always put your organization inside this string. And that's it. We have our org. And the AWS, we can go out. So after, we need to go in HCP Terraform. We need to create just first a new organization, so you can name it how like you want. After this organization, we'll create a new workspace inside. We can select the default project that is associated to our organization, and the workspace is created. We will go in this variable part in the setting on the left. We have two variables to set: the TFC AWS provider auth that will put the value true, and the TFC AWS one role ARN. So in the value you will put the role that you just created before. You should have something like that just after. And this is of course some Terraform variable. Okay. After, if when you create your Terraform workspace, if you select apply with CLI, you will need to put some Terraform configuration, the backend configuration that you put, typically the 3 or something like that. You will need to put the Terraform cloud and all your organization on the workspace. If you select that is Terraform that will read into GitHub, you don't need that. But here we'll put it, so I can just tap Terraform apply in my console. I will just need to log into to Terraform Cloud just before, of course, but it will apply just after. So we'll create our accounts. So here we'll create just 2 project accounts and the observability account. Okay. So that's something I think classic, I should already do it. And remember, after we need to create the CloudFormation stack set. So for this, we create a stack set instance, the resource. So the deployment target will be all the organization, our main organization units. And after just create the stack set, if you want the code of the IAM role or how to create with the identity provider, you have the link just here to get the CloudFormation template. So once it's done, it will be working. We'll be create a role that will be able to assume. But we didn't create yet our Terraform workspace for each account. Just before, you need to go on GitHub and to generate an host token that will be used by Terraform to read GitHub just after for the account. So that's what I put in the Terraform Enterprise Auth client. That's for GitHub. And just under, we'll create our Terraform Enterprise workspace. So I will run a loop on each account. The local for each account is typically all the accounts except the master one. So you put your organization, you put your project ID, and be careful, this is a project ID and not the project name. You can find it in the console, and you can give a name. Here I just want to have something that is readable for me, so, but if I go with just the account ID I find it, so that I put the ID and after the name that I give to the account, I activate the auto apply on the auto apply brain trigger, and I put just under, you see my GitHub repository that will be linked with the token, of course. And this is what we can do easily with if we use the community edition. That's what I love on the Terraform Cloud edition. This is the Terraform Enterprise run trigger. So I say that when the Terraform workspace account, so the will be triggered, a new one will be triggered when this Terraform workspace, the organization workspace will be over. So when an apply is finished on the master account, it will be trigger all the shield accounts. So if I change something in my stack, it will be trigger all the other stacks. And exactly like we did just before manually for the master account, we'll create the Terraform Enterprise variable for the provider and the role, and that's it. So normally at this step we have this project. We have the address organization index, that's my master account at the bottom, and we have the 3 other projects, as you can see. And you see that I'm just applying on the AWS master account, that's just for showcase you how it's working, and once the organization account is over, it will trigger automatically. I did nothing. That just Terraform on the conversion what we did just before, it will trigger all the accounts just before. Okay. Now, so we have our AWS master account that is provisioned. We have our project account that are provisioned, but we didn't provision our observability account yet. So for this, we create it, but we're not using it yet. We just create a role like the other, but we did nothing on it. For this, I need to create manually a provider for AWS for the region US East 1 and the region EU West 1. For this, I will use the organization account access role that is built in by AWS. And I can assume with my current role that I just used. For this, just after, we can create our CloudWatch sync. So this is the same each time as I use a provider, so that's for the readability, but if you have to use it, maybe you can use a module and to loop on the provider. Don't do like that, even if you have many regions. So here I just create the sync, and I also need to create a sync policy. I didn't put it in the screenshot, but if you want to see the sync policy, that's something that just like AWS resource, that's you can find it on the link just here. So that's it. As far as the observability account, we just create the sync policy, the sync link with a policy that say, okay, all the cheat accounts can send the data to this sync and not another organization, because I don't want it. But if you want it, you can do that. Okay, so we create the bottom, the sync, we need to create the link. So here I go on the second GitHub repository with chilled accounts. So that's the same thing. I create a link with my central link sync and my account name. I didn't mention it, but I have added a Terraform variable that's called central login sync from my first stack for getting this sync identifier that is generated when I create the sync. So this is a Terraform. This is a variable inside the workspace, and I put all the resource types that I want to send to this thing. And it's the same time I created for the AWS West East 1 on the AWS West 1 for Ireland this time. It was Paris before it was. And that's it. All the configuration I do just after the write. So if I go to the CloudWatch console on the monitoring account, now you can notice at the bottom top right that we have the monitoring account badge, and I can see that I've just run one lambda on each account. I have my first function, and you can see that it's mentioned that the account label is the tg-dev and with the account ID, and I have another logop, another lambda that come from another account. This is the Bauer one, with also the account ID that is different. It's not the same, and that's it. Thank you for listening to me. Don't hesitate if you have any question to write it in the chat, or even if you want to discuss a little more about the observability or other things like that. Or if you have a question, you can reach me on LinkedIn and send me a message. I will be really happy to respond to you. Thank you, everyone.
Thank you for this talk, Francois. We are so happy also to have you part of our HashiCorp Ambassador program. It excited me to see how you structured everything, and it's very similar to how I try to structure my my HTTP Terraform organization. And I'm definitely going to play around with an observability account. So thank you for that inspiration. I really liked it. Also, hey everyone tuning into the stream. It's great to have you here with us. You all are amazing. Now, in Terraform 1.6, we announced Terraform Test, a testing framework that allows you to create real but ephemeral infrastructure, and it's being teared down for you after your test has passed or failed. But Durrani is going to tell you everything you need to know about writing tests in Terraform. I'm really excited, but Durrani, the stage is yours.
Hello everyone, I am Narani Soundarya. I'm a senior infrastructure consultant in ThoughtWorks. I have an overall experience of almost 9 years, out of which I've been working in various cloud and DevOps projects for almost 6 years now. Now, over to the topic, let me share my screen. So the topic that we are going to discuss today is Terraform testing revolution with version 1.6. So anyone who has worked in infrastructure as a code would have been in this situation one time or the other. The reason being, this perfectly working code with all the perfect modules that works in dev and QA without a hitch fails in production for some reason. And there could be multiple reasons for that. There could be changes in environments. There could be, ideally that shouldn't, but there could be changes in the environment in which your code could be running that would have caused the issue. You could have predicted it. Sometimes you couldn't have predicted some of the changes. So the quest for confidence in getting or having a perfect Terraform infrastructure behavior has always been there. And usually what we do is we do a Terraform apply without the tools. That is, we do a Terraform apply when we keep our eyes open so that we do not miss even a single line that might have modified instead of deleted or deleted instead of modified. So we have to be on high alert when a Terraform apply happens in any environment, be it dev, QA, or production. So there are a lot of test frameworks that came and went. For example, you would have heard about Kitchen. You would have heard about TF Lint. There is a framework TerraTest. There are a lot of frameworks that come and go that tries to make this job a little bit easier, but it has been a little bit historically challenging. So Terraform introduced the Terraform testing framework in 1.6.0, but they've been providing support for us to have some form of testing in our code starting version 0.13.0, where we have the variable validation. Some of you might have worked on it, some of you might have not. They introduced this Terraform test command as an experimental Terraform test in version 0.15.0. So pre and post conditions were released in 1.2.0, Terraform checks 1.5.0, Terraform test command 1.6.0, and Terraform test command with box version 1.7.0. Why? I have titled this slide as the game changer Terraform 1.6 test framework. Why is it a game changer? Because if it creates actual infrastructure, so basically, when you have worked in a tool called Terra Test, you would have seen this. So underneath, that creates actual infrastructure that allows us to do a real world testing. Now it is offered within Terraform itself. It gives you tangible results. It tells you whether it was a pass or a fail. And it runs the plan and apply command for you. At the end of the day, it's a wrapper that runs the plan and apply commands for you and runs certain test cases against the output of the plan and apply commands. And there is no need for a third-party tool. The problem with the third-party tool is, if you think about it, let's say we are upgrading the version of the Terraform, or even let's say we are upgrading the version of the provider. This third-party tool that we are having should also support that. We have to keep the third-party tool updated. Maybe we are paying for it. We are having a license for it. Maybe we are not paying for it. It's an open source, but let's say someone introduced a huge bug, which now causes our Terraform test commands to fail. So there is a problem in depending upon a third party that comes into picture because Terraform did not have an inherent testing setup present before version 1.6. So the reason why Terraform became what it is because of its declarative behavior. What do I mean by declarative behavior? It means that when you write a Terraform code, you do not go and say, let's say I want to create an EC2, you do not go and say, first create VPC, then create the subnet, then create the route table, then create your EC2 security group. You do not tell them when to do what. You just tell, you know what, this is the VPC, this is the values that I'm providing for it, this is the route table, this is the subnets, and this is the Terraform EC2 instance that I want to create using Terraform. And Terraform takes care of creating that dependency and then creating the infrastructure that you need. In case of the testing framework, since it's also declarative, it makes our job very much easier because it follows the same flow as the Terraform code that you are writing. It has a seamless integration, and we don't have to worry about all the external tools, learning any new language for, just for using one tool, you have to learn an altogether new language. You do not have to worry about it. So since it's the same language, it has the same flow. So now for the purpose of the demo, this is what we are going to create in our infrastructure. Just giving you a simple architecture diagram. It's nothing but a simple EC2 that is running inside a public subnet, which is connected to a VPC and internet gateway. And finally, the Ubercool user, that is you, me, whoever is listening, we will be able to hit that endpoint and we will be able to see a web page, a simple hello world web page that I've deployed using an Apache web server. So before we go into the Terraform test and the demo and all that, I wanted to create an imagery where the infrastructure that you want to create, compare it to a castle. And hawk-eyed people who are fans of Harry Potter would have recognized this picture. It is actually Hogwarts. And for people who do not know Harry Potter, it's just a castle. Think of infrastructure as a castle that we want to protect from enemies. So the first protection that we can give to our infrastructure castle would be a gate, right, where we do not allow certain people to enter. So similarly, input variable validation is very similar to that kind of a gate where we keep a validation at the variable level to not allow certain values to pass through the Terraform code that we have written. So if you can see the example here, we have a variable, my public IP. I do not want the values supplied to this variable to be 0.0.0.0/0. Why? I do not want it to be open to the world, even accidentally. So what I do is I keep a validation for that variable and I add the condition. It follows this format. I have to add a condition and I am making sure whatever value supplied to my variable.public IP is not equal to 0.0.0.0/0. And if it is provided, then the Terraform plan or apply should fail with an error message. CIDR should not be open to the world. This is the first line of defense. Owing to the time, I'm not going to show a demo for these except the Terraform test. So let me move on to the next defense that we have. So this is the pre and post condition. And again, if you're a Harry Potter fan, you'd know this. This is the Whomping Willow. And for people who do not know, it's just a tree that hits people that comes nearby. I have a certain reason why I kept this as a protection or something like that, compared it to the pre and post condition. Let me come to that. So pre and post condition is a way in which you can add conditions to the Terraform flow and make sure that it is working as expected. But unlike popular belief, Precondition does not work during Terraform plan. A lot of people think that precondition, when you do a Terraform plan, precondition comes into picture. When you do a Terraform apply, postcondition comes into picture. That's not the case. Precondition is done before the particular, let's say you place a precondition in an EC2 instance block. Precondition comes into picture before the object gets evaluated. And postcondition comes into the life cycle after the object gets evaluated. Simply to say, let's say I want to create an EC2 instance. I want to make sure that the subnet in which the EC2 instance is launched is public. Then before the EC2 instance launches, add a precondition block to the EC2 instance block. And that way I make sure that before the object gets created, it evaluates and fails in case of any issues. In case of postcondition, let's say I have launched the instance, but I just want to make sure that the public IP of the instance is available. So in that case, once the object gets created, postcondition comes into picture. So if you can see this example, I put it into a lifecycle block. It follows the same pattern that we saw in variable validation. You have a precondition, you have a postcondition. You have a condition in which you have the use case in which you want to test. For example, here, like I said, I'm testing whether the subnet that I am supplying to the EC2 instance has map public IP on launch attribute as true. If it is not, fail it before the EC2 instance gets created. So after the EC2 instance gets created, I just want to make sure that, let's say in this example, I'm just checking if for the route table, whether the subnet ID associated in the route table as a public subnet is the same public subnet that got created through the AWS subnet creation process. So this is how we can make sure that we can test it. Why did I keep a warping willow for that? Because pre and post condition kind of terminates the life cycle or the way in which the things are happening. For example, for your EC2 to get created, you would have had a VPC route table and all of that. And let's say in case of any failures here, it will stop the flow then and there. Like VPC would have been created, subnet would have been created, route table would have been created, but then EC2 has an issue, so it will stop it right away. So this might cause some issues because it abruptly stops the flow. And that's why I had a warping willow as an example. To overcome this issue, there is one more check or one more security kind of a thing or testing kind of a support that Terraform offer, which is checks. And again, sorry for non-Harry Potter fans, but if you're a Harry Potter fan, you'll know this. This is a three-headed dog, which will sleep when it hears music. Even though it looks very dangerous, it will sleep when it hears music. So it's not that dangerous. It becomes like a normal dog. So checks I added. So this is where Terraform introduced checks, where if you see, it again follows the same format, which is condition and error message, except that the surrounding block is different. I have a check block with a logical name, and then inside the assert block is where I have the condition and error message. So the advantage of this over pre and post condition is that this will just warn you. This would not stop the flow. So any chance that the resources might get tainted will not be happening in case of checks, because as soon as you do a Terraform plan, it will show if the error message, if there is a problem, it will show as a warning that this is a problem. And as soon as you do a Terraform apply, the same. So it is irrespective of the life cycle of the resource, this will work and you will be able to get a proper understanding of whether whatever you intended happened or not. Cool. So the fourth defense for our infrastructure castle is the Terraform test. And again, if you're a fan of Harry Potter, you would know the scene where in the final book, to protect the castle against Voldemort and his supporters, McGonagall utters basically a chant, and then this person or the soldiers from the infrastructure castle jumps out and protects it. Truly a goosebumps moment. And I just wanted to highlight Terraform test, and that's why it's there. So before we go into a demo, before we go into examples, I just want to cover a little bit of theory and then we'll go there. So the Terraform test command processes Terraform testing file and executes contain test. So all the Terraform test command does is it goes to a file called dot with the suffix .tfTest.hcl, where the test cases will be written, and it will process them and validates whether the test cases are passing or not. And Terraform, they keep their own state in memory. Why is this important? You might have a question. In a couple of slides before, you would have mentioned, you would have seen that it creates actual infrastructure in the backend, right? So in this case, Terraform test keeps its own state in memory, separate from the actual state of the rest of the infrastructure. This makes sure that whatever we are doing in the Terraform test does not disturb the actual infrastructure state. So the Terraform test command creates real infrastructure, and once it's done, like once it's evaluated everything, whether it's a pass or a fail, it will go ahead and delete any remaining infrastructure. Here, I want to call out one thing. Sometimes all the resources did not get deleted, but it will show in case of some failures, it will show that these resources are not getting deleted. So we might have to manually go and delete them. But this did not happen a lot of the time. This happens sometimes. So keep an eye out for that. So in Terraform, the default behavior, let's say a run block that I'll explain in a minute, the default behavior is apply. So when I have a run block, automatically Terraform underneath the wrapper does an apply command on your whole infrastructure, unless and until you specify that it should be a plan. When should I go for a plan? When should I go for an apply? So the plan can be used for situations where you just want to test the logic, and you can use apply commands in situations where you want to test whether the actual infrastructure related, integration related use cases can be tested. So now, so this is how a typical Terraform test folder structure looks like. If you can see, it is the normal. If you've worked in Terraform, this looks very similar to what you've already done. You will have a data.tf, main.tf, whatever structure that you're following. The highlight is the test folder with the demo.tf-test.hcl, where, as you can see, whatever test files that we're writing should have the suffix .tf-test.hcl. So now there is a variables block in which you can supply additional variables to your test by overriding the default values. You will understand in a minute. So it supports variable blocks at both the root level and within run blocks. Terraform passes all variable values from the test file into all run blocks within the file. So what it means is that you can basically override the variables that you are getting from your default variables.tf by supplying it inside the test file itself. Consider this example that I've added a screenshot for. I apologize for the color here because this is happening because of VS Code not supporting this particular version of Terraform yet at the time of my recording. But if you can see here, this is how a typical test case will look like. It starts with a run and then whatever logical name that you want to give to your test case. And then, as I mentioned, you can either do a plan or an apply. Plan for logical, any test in the logic that you've written, and apply for integration testing. So here I want to do an integration testing. So I have command equal to apply. And what I'm doing here is that I am overriding the values that are coming from the variables.tf with the variables block. And this is the variable name that I'm overriding, which is default tags, where I'm adding name test demo. And I have an assert block. Again, it follows the same format if you've been following: condition, error message. And on the condition, what I'm trying to see here is that whatever variable that I am supplying, for example, variable default tags, I am looking up for the key of the tag, whether it's the same as the one that is applied to the AWS instance as well. So what it means is that when I have a run block here, underneath, since I have command equal to apply, it would have done a Terraform apply on the whole infrastructure code here, and the output would be considered here. And this output is the same as the variable that I am supplying. This use case that I'm particularly sharing might sound very simplified, but this is for the purpose of the demo. You can expand it to any use case that you want. You can make sure that the AWS instance has the name tag, probably because of FinOps or any of the reasons. You can make sure you can introduce any number of conditions here. And if it fails, it will fail with the message tags are not properly added to the instance. So I want to make sure that my instance has a name key with the proper value to it. This is a way to achieve it. So this is how a file syntax would look like. Let's consider one more example. Run is equal to the word. Here, I do not want to do a command equal to apply. I'll tell you why. Again, I have an assert block. I have a condition and error message. Here, I'm making sure that my public IP that I'm supplying as a variable is not 0.0.0.0. So why is it a plan? Because even before the actual objects of the Terraform resources get created, you will know the variable, right? You will know even before all of this. So here is where I want to use plan. I just want to make sure that, let's say, accidentally someone supplied 0.0.0 in the default values file, then this test case will automatically fail. Let's say if think about a scenario like this where you have this Terraform test as part of the CI part in the building of your Terraform code and deploying it. There, if it fails, you can make sure that no one has supplied. You can make sure that no one supplies an IP that is open to the world, making your whole code more secure. And this is another test case. Try to be with me here. But before that, let me share a variable validation that we have so that we understand that test case better. If you can see here, variable AMI, what I'm trying to do here is that I am getting the Amazon machine image in a variable called AMI, and I had added two validations. Both of them ideally does the same. That the reason that I had added two validations is because just to show you folks that you can add more than one validation to a single variable. Here, if you can see, I'm just making sure that whatever value that I'm getting for the AMI variable has a length of greater than 4. And the substring, the first 4 characters should be AMI hyphen. This is the validation that I'm having. The second one does the same, except it does it using regex. Now back to our setup here. So if you can see here, this is a test case. Bad AMI ID should fail is the logical name that I'm giving it. I want to do a command equal to plan because this kind of a validation happens at the variable level itself. I am supplying a wrong value intentionally, and I'm making sure that the variable validation is in place. And if, let's say, if I supply this value, what will happen? Underneath, it will do a Terraform plan on the code. This value will get substituted there, and the variable validation will fail. And I add an expect failures. So if it fails, it is expecting failures. So this test case is a success. So the reason that I wanted to highlight this is because this is a way in which you can test, let's say, your variable validations, your pre and post conditions in your code, and make sure that accidentally none of it gets removed. Let's say a fellow developer who is working on this code realizes that, you know what, this variable validation does not make sense. Let me just remove it. If they remove it and you do not want it to get removed, you can add a test case like this and expect failures from it so that this test case will fail if the variable validation is not present. You get what I'm saying, right? So this expect failures, since it's expecting failures and we supplied a wrong AMI ID here, this test case will become a pass. We can also write Terraform test against modules. Previously, I mentioned that when you write a run block, underneath it does a Terraform plan or apply on top of the whole code. Let's say you want to restrict it to just a module and you do not want to run on top of the whole code, you can write it for a module as well. As you can see here, run block again, module demo is a logical name that I'm giving. I have a few lines commented here just to show you folks what is possible. So there is a reason I have a providers block here. I'll tell you in the demo part. But let's say I'm overriding all the variables that I'm supplying to the module. I do have a module in the original Terraform code that creates an EBS volume. So what I want is, I do not want to run Terraform. Let's say I do not want to run Terraform test on all the code, just the module. Then it is possible by having a module block and specifying a source variable to it. There is one more variable that you can assign to it, version. But at the moment of recording this call, the source supports only local modules as well as Terraform registry modules. Let's say you host your modules in a GitHub location or a remote repository. It was not yet supported. Hopefully it will get supported in the future. And whatever values that we are supplying to the module, we all have worked with modules, right? Whenever we want to deploy a module, we supply all the necessary variables that is needed for the module. You have to supply it with the variables block outside it. This way, this Terraform test case runs only against the module. Now over to the fun part, which is the demo. Because of the time that it might take, I am going to show just the, one second, let me hide this. Okay, cool. So I'm going to show just the output of a previous test command that I had. You can see a few failures. Hopefully, if we get a failure, we'll be able to figure it out. We'll, in fact, debug it on the pipeline. As you can see, this is how a typical Terraform test command output looks like. Let's wait. It takes some time. So we'll go to the code and then come back to it at the time this will be working. Cool. Let me go to the code. So the one that we are going to see now is Terraform testing 1.6.0. Let me close all the folders. And if you can see here, you have your typical Terraform testing 1.6.0 code where you have all the files that we just saw just a few moments back. And as you can see here, I have a test folder where I have certain tf-test.hcl files. And if you go to the main.tf, it's nothing but a creation of an AWS EC2 instance, and it creates an EBS volume. And if I go to the modules folder, I have the EBS volume created here. And I have the EBS volume created here. And as you can see, it's very simple. It has a few variables like default tags and AZ that I'm supplying. I'm creating an AWS EBS volume. And once it's created, it's just the output is just showing your EBS ID and EBS taxon that we can access from the main.tf if we want. So this is the structure. Let me go to the tf-test.hcl. Again, I apologize for the color coding. It was not yet supported. So I'll try to explain this. As you can see, I have a provider block here. Why do I have a separate provider block here? I want to highlight this region AP South 1. If I go to the variables.tf, the original code, that is the actual infrastructure, gets created in US West 1, Oregon. And I want to deploy this whole thing in the new region altogether. There I am using AP South 1. Let's say I want to run all of my test case in a new region altogether. That's where I have that. And the typical provider related configuration, I am having it. This is similar to what we have in the actual provider. As you can see, I have a variables block here. Whatever variables that are coming from the variables.tf, this particular variables will override it, and whatever variables that are here, if you have variables inside the run block, that will override the variables that are provided in the root of the file. This is one test case that I can highly suggest. For example, I have commented out the providers AWS equal to AWS ABCD. There is a reason. Just like this, you can have one more provider, add an alias. Let's say the alias name is ABCD. You have a situation where you feel like, let's say, I want to run, I have 10 test cases. 8 of them I'm fine with running in Mumbai, but 2 I want to run it in, let's say, Singapore is the region that I want to run it in. You can have multiple provider blocks and use alias like this so that it can run in multiple regions. Just to show you folks that it's possible, I have it, but for the purpose of the demo, we are not going to see it. I have a command equal to apply, and in the condition, I'm just making sure that the AWS instance that gets created when this run block does a Terraform apply has at least one tag. This just checks if there are no zero. If there are no tags available, this condition will fail and it will show the error message, tags are not properly added to the instance. Similarly, this is something that we saw on the slide itself, valid key of tags. I'm not going to explain it. Is public IP assign, again, something that we saw on the example in the slide deck. Is open to world, these open to world we saw on the slide deck. Is public IP assigned? What I'm doing is I'm just checking if AWS instance demo.public IP is not equal to empty. I need the instance's public IP to be available for me to hit the web server so that I can see the web page. So this is a condition that I wanted to add there. In case it fails, it will come up with an error saying web server will not be accessible as the public IP of the subnet is disabled. So run bad army ID, something that we already saw. Let me go to the demo module tf-test.hcl. Again, very similar structure. If you can see here, this is the run block for the module. We have the module demo. Again, just added this so that to tell you folks that it's possible to have multiple providers. Here, whatever variables that I need for the EBS module, for example, let me open it. If you saw it, it needs default tags and AZ. I am supplying that here in the variables block inside the run block where I'm calling the module block. So in the one module block, you can see that I have the source where it points to the EBS module and run verify module demo. So here is where I'm running test cases against that module. What test cases am I writing is that, let's say I am supplying, I can override the whatever values that I'm supplying here, and then I'm supplying certain values here and I'm doing a command apply. I just want to make sure that the module demo EBS tags or whatever that this module is outputting, EBS tags all, if outputting is a word. So whatever this module shows as an output is the same as whatever I'm supplying here. Ideally, this would not be the test case that you'd be writing, but just to show you folks that this whatever variables that I'm supplying for the default tags overrode the values that we are supplying from the, for example, if you see the variables.tf, the default tags value is just 1 here, right? So ideally, just to show you folks that whatever we supplied here overrode the original value, I just added this test case. So run module demo. How can I access the output of this block? Is run.module-demo.ebs tags all is nothing but the output that the module outputs. So run module.demo.ebs tags all equal to 3. Now, if test condition passes, it means that whatever we passed as variables got passed. Ideally, this would not be the use case, but just for the demo sake of the demo, I am showing this example. Again, I have one more asset condition which I've commented here. If you can see here, I am accessing the actual module.demo.ebs tags all. Just to show you folks again that you can also, when you write a run block, underneath it runs your Terraform apply. I can access the output of the Terraform apply just like you would inside the Terraform code itself. Let's say the module gets created, right? You would access it like module dot name of the module dot whatever the output that the module is exporting. Similar fashion, you can access it and then make sure that whatever values that you are supplying is passing or not. So, and the next valid key of tags, it is very similar to the one that we saw during the slide deck, so I'm not going to explain further. Hopefully by now it's completed. It says planning failed, probably because it's an internal error, but as you can see, the test cases are a pass. All of the test cases are a pass. Let me do it without a verbose command also to see how it looks like. It might look like a lot, but underneath what happens is that it creates actual infrastructure. And once it has been created, it will go ahead and then terminate the infrastructure that gets created. So let me go to the top of this. Okay. If you can see here, the first one, it ran through module demo module tf test.hcl in progress and it passed. And as you can see, it created just the EBS volume that we referred to. And the output of the EBS volume, as you can see, matches whatever values that we supplied here. And the second verify module demo, since we have an apply, it went ahead and then created the whole infrastructure and it would have run our test cases on top of it. Okay. And similarly, if you scroll down for the other test cases, it would have created the infrastructure and destroyed it. So you might have a question. So does it create infrastructure for every run block and destroy it? No. You will be able to understand it when this one completes. So what happens is that whatever you are trying to, whenever we are dividing the test cases into separate files, it also separates the state files within them separately too. For example, this particular file will have a separate state file, and this particular state file will have a separate state file. And internal references are done from that state file. So why is this important? So logically separate your test cases in files so that it does not take a long time for it to create and destroy. Let's say for the test cases, if I have individually in separate files, it would create and destroy. That will take a long time. So to avoid that, as you can see, this is a very good example. Demo module tf test.hcl. It was able to run certain commands, and as you can see, it is tearing down what it created. So it kind of groups the test cases in one single file, creates the infrastructure, tears it down, then groups the test cases in one single file, creates the infrastructure and tears it down. So this is how it works. Cool. Okay. I passed the video so that you folks would be able to see how the final output of the Terraform test looks like. As you can see, first file, everything is passed, and then it tear it down. So it went to the second file, tf-test.hcl, everything was a pass, and it's tearing it down. So once it is success, it will give you a tangible output, something like this: how many passed, how many failed. You can use this in your CI pipeline accordingly. Now over to the second part. An interesting use case or situation that they offer is Terraform testing with mocks. Anyone who have experience with mocks in a traditional programming language, you'd be able to relate to it. If not, don't worry, I'll help you try to understand it. So this person, again, in the Harry Potter world is August Filch. He's also a part of the security. He makes sure that no one enters the premises without a proper permission, but then he's not actually, even though he shows himself as someone with magic, he's not. It's a mock, right? And that's why I took that example. Again, sorry for non-Potterheads. So Terraform test mocks, it's still in beta by the time I was recording. So Terraform test feature the mock provider block, enabling you to simulate the provider's behavior. What do I mean by that is that when you are writing your test cases, there could be a situation where you want to test just the logic in which your test cases are written. You don't care about connecting to AWS. It takes a lot of time. It probably costs you as well. You just want to make sure that whatever local block logic that you've written in local block, your for each blocks and all that are working fine as expected. In that case, you can go ahead and use Terraform test with mocks. I can mock the overall AWS provider itself, in this case AWS, so that the connection does not even go to AWS. It will just give you a valid response, and using that valid response, you will be able to test your logic and make sure that everything is working fine. They replace real provider in test, sharing the global namespace, allowing for realistic data generation. What do I mean by realistic data generation? We'll see in a minute. So it has to mock the values for it to be realistic, right? Let me close this and show this. I have written a test. I'll show this and then I'll get to why I say that it's realistic. So if you can see the output of the Terraform test command that we just ran, you'd be able to see, let's focus on this one, right? You'd be able to see some dummy values. In ARN, it is showing 1HX. In it is encrypted, it is showing false. ID, it is showing some dummy values. And let me run this again. Terraform test without the verbose. Previously, it took us at least 2 to 3 minutes for the whole test case to pass, right? Here, since we are mocking the provider itself, the connection is not happening to AWS. It's just a logical check. See, look how fast this is because it is not actually connecting to the provider. And as you can see, it provides dummy values. What is the format for the dummy values that it provides? So numbers by default will be 0, booleans will be false, strings will be a random 8-character alphanumeric string that we just saw. Collections, including set, list, and maps, will be empty. Objects will contain required sub-attributes generated using the same set of rules. So I can, but let's say in your logic, there is a situation where you are taking one of the mocked values, let's say one of these values, and you are doing something with it. But if it comes as a mocked value, it will create problems in the logic itself, right? So there, you can actually mock the provider, and for certain values, let's say you want to provide actual values. Again, if you saw the output that I just showed you before, availability zone is US West 1A. Let's say there is a logic in my code which checks whether it's US West 1A or not. If it gets a dummy value, it will fail, right? So I want to override a particular variable alone. That is possible. Let me show it to you folks. So this is how, no, in a minute. But this is how a mock provider will look like. You have to add an alias so that it is differentiated from the actual provider, and you have to provide a source where you have written your mock files. I'll show what a mock file will look like. Just like for test cases, you have written tf-test.hcl files. For mock files, you have to have them in .tfmock.hcl file. So we are running a test on them, and then highlight on this part where I am referring to this particular mocked provider using AWS equal to AWS.name of the alias, which is mocked. And then you can write your conditions as it is. So let me show how it works before we move on to the next part. So if you can see here, I have this file. It looks very similar to what we just saw before. So if you can see here, I've commented out certain code. So how can I mock certain values to show that particular value that I want? Let's say your logic depends upon one of these values. I don't want it to be a dummy value. You can do so by, let's say on the AWS instance, I want to mock the return value that I'm getting for the availability zone. It is possible for you to go ahead and then add it in this block, which is the defaults block, and whatever values that you want to have, the values that you want to provide, you can add it to the defaults block. Let's say on the availability zone, I want it to be ABCD. For some reason, I want it to be ABCD. Then what will happen is that when we are using this, whatever values that we are getting, that particular value alone will be mocked to whatever value that you are providing. Okay. So in the tfmocks.hcl, if you can see here, I have an AWS folder under which I have the tfmock.hcl file I have added, and here I can, we mock the provider. Now we want to make sure that certain values are the right values. The rest I don't mind. Certain values are the correct values that I want. You can do so by adding the mock resource, mock data. You can mock your resource, you can mock your data. Similar fashion, you can mock these blocks and provide certain values. Cool. Now let's move to the second part of this, which is override blocks. So let's say I don't want to mock the whole provider. I just want to override particular block. Consider the scenario of where you want to create an RDS instance as part of your Terraform code. Usually when you worked on a creation of RDS instance, it takes 15 to 20 minutes max, right, for it to come online or available. Let's say you are running your test cases a lot more frequently. You don't want to do that. You are confident that the AWS RDS resource will get created. I just want to override that creation so that the rest will function as it is, and I don't want to worry about the time taken for the RDS. So you can do so by overriding the RDS resource using something called as an override resource block. There is also an override data block. Let's say you are connecting to AWS SSM for getting maybe your some kind of a secret, some kind of a value that you're storing there. But every GET request is charged. You don't want to do that for every test case that you're writing. You can override the data block where it connects to SSM. You can, similar fashion, you can override modules, and you can use this in order to mock the values. So this is how a typical override block looks like. I've shown an example of override module. Here, I am overriding that EBS module that we saw. The name of the module is demo EBS. So module.demo EBS is the target that I want to mock. And what is the output? It will give some output, right? The EBS module will give some output, right? I want to make sure that this is what I get from that. Let's say EBS ID is equal to ABCD. EBS tag solve, this is the tag that I'm getting. So that when the actual flow goes, instead of connecting and creating the actual EBS volume, it will use this module override module block, and it will give you some dummy values so that you can proceed to the next step without waiting for that resource to get created. This is an example of overriding data. As you can see, it has a target too. Let's say I want to override a data target that gets some details about the instance. And let's say I want to override the value that it's providing, AMI hihi, right? Cool. So like I showed under AWS, what is the provider name? Under that, you have the demo.tfmock.hcl where you can provide any specific values. Let's go to the demo for the second part of the mocks. For this, let me comment this out so that I don't run this. If I have this file, right, this is where I have the mock provider. It will mock the whole provider. I don't want to do that. I just want to mock a particular resource. Before I go and explain the code, let me run this because it takes some time. Let it happen in the back end so that we'll go ahead and then go ahead through the code to understand what is happening. So here, provider AWS, I have variables. At this point, you would have been familiar with this. I am overriding the module so that whatever output that I'm getting from the module should be following this value. I'm overriding data too, which we just now saw. So how am I writing test cases against them? Let's say I'm writing test cases against them like this: run verify module demo mocks. What happens underneath is that it will do an apply command on your whole code, but instead of going and creating that module, it will refer, since we have written an override module, it will be able to get that output that the override module is giving. And here I've added a assert condition. If you can see, I'm making sure that module demo.ebs tags all equal to 4, just to show you folks that this module got overridden. Let's say I have one more tag which says tag 5, whatever, some dummy value. Then if I put 5, then it will match because now the module got overridden by your setup. So why is this? There are multiple use cases in which you can use it. Like I said, you can use it in place of an RDS. You can use it in place of, let's say, an EKS cluster. You want to save money, you can use this approach. Again, I am making sure that the module override data is also working as expected. How? So basically, verify override data, a logical name. I'm supplying some values here, and I want to make sure that whatever instance that gets created, the data data for that I'm getting, then AMI should be he, because this is where I've given overriding the value that it's providing, the output that the data block is providing with he. So I'm making sure that it is working as expected. So this is how it looks. Like I said, since it's not, we have not mocked the whole provider, we are just mocking certain blocks. So the whole infrastructure gets created. Only the part where we overridden, let's say the block and the data resource got mocked, and that's why whatever test case that we wrote are a pass. Cool. I hope you would have got it. I want to end it with a few insights that I got while working with this. The infrastructure is created and destroyed per tf-test.htcl file. An asset block runs a Terraform planner apply command underneath, irrespective of whether you use it for testing purpose. What do I mean by that? Irrespective of whether you have, let's say, a condition here or something like that. If you have a run block, it runs your Terraform plan and apply there. And Terraform test file only support local registry modules. At the moment, maybe remote modules are not supported. Only if you have referring to Terraform registry modules, then that's supported. For mocks, override resource can be used to override a specific resource to save some time, which we've covered. While Terraform executes a Terraform test command, Terraform maintains at least one, but possibly many state files within memory for each test file. Cool. If you folks have any questions about this whole thing, please reach out to me. We are at the end of the discussion. Please ping me. I'm available over LinkedIn, or you can even ask in the place where you are seeing this video. I'll try to see if I can reply to them. Thank you.
Thank you, Dharani. I really enjoyed this talk, and I'm sure I'm not the only Harry Potter fan here, because those analogies were awesome. Now, input variable validation, checks, pre and post conditions, and Terraform tests are key to deploying reliable and predictable infrastructure. Do you agree with that, Karim?
I definitely agree with validating things. I also agree with people not revoking policies midstream and killing tokens. But other than that, yes, very great talk. Love it. It makes your code stronger, right? And I think that's always important.
Exactly, and it's good to have you back, Karim. Really, it really is. So yeah, having the ability to continuously validate your infrastructure with these features reduces potential misconfigurations and the time to detect issues, right? And also, if you're part of a team that provides modules as building blocks to other teams, being able to test your own modules and making sure that you don't introduce breaking changes to those internal end users is crucial.
Or to policies.
Exactly. Now, our next speaker is going to talk about Earth observation. Is this something you've heard of before, Karim?
I mean, I do like hanging outside, and then taking my drone up and looking down at the Earth and thinking, hey, you know what, this is cool. I'm sure Armagon is talking about something else, but I'm curious, what's in store for us?
Yeah, good question. So to me, it's also completely new. But our next speaker, Armagon, is going to talk about the challenges of processing Earth observation data and how Terraform plays a big role in the Earth observation community. And wonder why? Armagon, the stage is yours.
Hello everyone, my name is Arman, and today I will be presenting a session called Terraforming Earth, how Terraform bridges the multi-cloud gap for the Earth observation community. And this is me, my name is Arman Karatosun, and I am Cloud Data Access Services Expert at UMESAT. You can of course reach me from my social media. Before going any further, I will start by introducing you to the European public space sector, but I must say that I do not hold any official position to represent any of the institutions that I mentioned below, and the information that I'm sharing is just the available online available information. With this in mind, let me introduce you to the ESA, or European Space Agency. Well, it is Europe's gateway to space. ESA works together with the national agencies, institutions, and organizations, and has 22 member states. ESA coordinates several missions and programs, most notably Copernicus program and Galileo, in close coordination with other agencies. EUMETSAT stands for the European Organization for Exploitation of Meteorological Satellites, and it operates satellites for monitoring weather, climate, and the environment. EUMETSAT works together with national agencies as well, institutions and organizations, and it has 30 member states. EUMETSAT operates several series of satellites, including Meteosat and Sentinel series, and it also has a data archive and online data lake, which contains more than 10 petabytes of data, spanning more than 300 products. I also would like to highlight that I worked at EUMETSAT as cloud computing engineer between 2019 and 2022, and now as cloud data access services expert since July 2024. ECMWF stands for the European Center for Medium Range Weather Forecasts, and it provides 24/7 operational service, producing and disseminating numerical weather predictions to its member and cooperating states. ECMWF hosts high-performance computing facility as its core of its operations, as well as meteorological archival and retrieval system called MARS, which provides access to meteorological data that has been collected or generated at ECMWF for almost 40 years. In addition to that, ECMWF also hosts a cloud infrastructure in close coordination with HPC-related activities. I also would like to highlight that I worked at ECMWF as cloud computing engineer between 2022 and 2024. Of course, these institutions work hand-to-hand with other institutions such as European Commission and European Union and partners from the private sector. Well, let's talk about Earth observation data and its history. Let me tell you, it's a bit complicated. It all started with FTP server in the beginning, or an NFS share or threads data server, but everything has changed when the Cloud Nation attacked. Since the launch and success of the Copernicus program in 2014, the amount and the size and the quality of the Earth observation data that we gathered from Copernicus satellites, which are called Sentinels in this case, they grew enormously and significantly. And this led to an emergence of several cloud-based services, mostly residing in their own data silos. You can learn more about Copernicus series in the link down below. Well, the access and data discovery for Earth observation data is quite diverse, I must say. At EUMETSAT, we have EUMETSAT Data Access Services, which has data store APIs, and EUMETSAT Data Access Client called EMDAC. We have ECMWS Meteorological Archival and Retrieval System, MARS, and Production Data Store, ECPDS. Both of them has data APIs and clients. And we also have Climate Data Store, which is maintained by ECMWF, part of Copernicus project, which also has different set of APIs and clients. On the other side, we have Earth Observation Gateway and Copernicus Data Space Ecosystem. You can learn about them in the link down below. But why this is a problem? Well, trying to learn about different API systems, trying to learn how to authenticate them, trying to learn how you discover data or access data might be quite challenging. And most of the time, our meteorological institutions handling different data sets from multiple sources. So, for example, they are handling climate data from EUMETSAT, but they also need forecast data from ECMWF. They are also increasingly doing things with Python nowadays and using data processing frameworks like Dask. So having multiple data access methods might be challenging for them. They also face increasingly large data volumes that needs to be downloaded and moved across the systems, because most of the time they already have some kind of an internal or external computing facilities that they need to download the data and process the data. Well, what about data federations? Well, I must say, good luck with that. Let me present you the idea and the challenges underneath it. So harmonized or federated data access aims to provide Earth observation data access, discovery, and sometimes processing on different collections and products available under different providers. And I must say, this was a never-ending dream of ours. So in right-hand side, in the image, for example, you can see an example called EODAC, which has different data collections from different providers, and it offers APIs and clients to access them. And we have many others. We have Wikio HDA for Copernicus data. We have OpenEO, which is becoming slightly different, but really relevant, we have destination.hda, and we also have EODAG, as I mentioned. But you can see, you can probably quickly realize the problem with it. You are accessing a data set from an harmonized data access to another harmonized data access. So we put HDA in your HDA, so you can query while you can query. I must say, guys, this can raise some scalability issues, and I have some bad news as well. I believe personally, we will never have a harmonized data access. So cloud to the rescue. Well, kinda. We had an idea. We thought if they cannot afford moving to data, we can let them compute near to the data. And this is how European Weather Cloud is born. Okay, I must say there are also similar clouds providing access to different collections such as VKL, a European Union service for Copernicus data. But the idea is to simply move users near to data by providing computing resources. This is often called infrastructure as a service, allocated to their tenancy. You can think it as a community cloud where Earth observation data processing community can come together and access to EO data. So, European Weather Cloud, or EWC for short, is operated jointly by EUMETSAT and ECMWF, and it's based on OpenStack. So the idea is to have authorized users using similar interfaces and tools, creating virtual machines on either cloud that they have access already. So one example might be to have an ECMWF VM that digests downsamples and transfers only the necessary part of the data to a VM that runs in EUMETSAT, which does the satellite processing. I must say the data still stays in the silo in the respective cloud, and it is being accessed via the traditional formats, which I will come to that later. But this is already a huge way forward in how we do things with HDA, for example. But what about use case? What about the use cases that we need equal data from 2 or more parts of the cloud? One example might be to direct pixel by pixel comparison of a model and satellite observations. Well, this is still an open topic, but this was the best idea that we had so far. We also realized that there are some activities going on public clouds which can afford to move the data, and they also have a lot of compute. I must be honest with you folks, we cannot compete with the hyperscalers, especially on the computing part. And they already offer Earth observation data catalog to their users in cloud native formats. I will come to that later. Most of our users already are using or accustomed to at least one of the public cloud providers, and they are offering standardized APIs, for example, S3, to access and discover data. And they are becoming more popular and popular. And to be honest, they did move a lot of data. On the left-hand side, you can see Era 5 data in cloud-native formats, originally coming from ECMWF, from Microsoft Planetary Computer, and from the right-hand side, you can see Google Earth Engine data catalog, which has Sentinel collections in cloud-native formats. I must say that this is a huge step for public cloud users where they have access to data already and they can use the standardized APIs and the seamless integration that they have on the public cloud. But without going any further, let me stop by and talk about the data a little bit and cloud native data formats, of course. So what are they? Cloud native data formats, such as ZAR or cloud optimized GeoTIFF, they are structured in a special way to enable users efficiently retrieve data from cloud object storage, such as S3, to allow n-dimensional data access. But what does it mean? So in a traditional way, in order to access the data, you need to download the data in a legacy format. Let's say it's an FCDF file, although NetCDF is quite recent. So in order to get you started with the region of interest or region or the value that you are interested with or the variable that you're interested with, you need to download the collection and extract that kind of an information from the NetCDF file. You're already required to download the data, which might take some time, and then extract the region of interest and start processing only then. This is a fundamental change that we are witnessing with the cloud-native formats, which changes the traditional paradigm and allows users to access these chunks without storing and downloading or copying tailored data to start processing. It also enables users to rely on well-established data access and discovery APIs, such as S3, instead of trying to learn different array of software libraries, such as HDAs. So, multi-cloud to the rescue then. Well, one might argue that this might be the end for the community clouds. I think not really. I only think that we are at a critical point where we can transform the way we are working with Earth observation data. First of all, not all Earth observation data is available on public clouds due to several challenges on feasibility, the data is simply too big, or other practical limitations. But we can foster collaboration with public cloud providers to provide secure and platform agnostic ways to interacting with the data by implementing generic cloud native workflows. On the right-hand side, you can see an example where we published under the blog post in Dusk blog. You can access the link down below for details. But in an essence, we had in that prototype, which is called Data Proximate Compute prototype, two different clouds, one community cloud, European Weather Cloud, and one public cloud, Amazon Web Services. And European Weather Cloud has essentially two different clouds, EUMETSAT and ECMWF. We were using Amazon to host the client computer, in this case, a Juniper notebook. And we have attached the data that are available locally on ECMWF and EUMETSAT to ECMWF and EUMETSAT worker nodes to have local data access. Well, by embracing the simple distributed logic, we already stepped up a lot without even embracing the cloud-native formats. So as you can see, we still mounted the data with NFS using traditional data formats. But on the right-hand side, which I will be explaining in detail, you can see a task screen with some numbers taken from the calculation. And if you look down below, the ECMWF workers showed in green, doing the bulk of reading and computation, while the red transfer tasks in the task screen joining with the data reads on EUMETSAT side. And this already reduced the calculation time from 14 minutes to 10 seconds with a feasible reduction on the measured network traffic. So we were copying less data and the calculation was taking lesser time. So this shows a community cloud in combination with one or two public cloud can work. But how we can mitigate the complexity of running a computation on multiple clouds? Well, this is how Terraform comes in and how Terraform bridges the multi-cloud gap for Earth observation community. Let me start by highlighting the feasibility of using Terraform in simplifying operations on multiple cloud, of course. So Terraform essentially providing us the much needed flexibility to consume Earth observation data or simply deploying infrastructure on multiple clouds. So by providing integration with almost every type of public/private cloud available with providers, Terraform makes our lives easier to deploy things without even need to develop additional tools on top. Of course, specialized workloads can be further offered by providing modules in form of Terraform modules, maybe tailored to the Earth observation community. But what I want to highlight is that this is not needed because we managed to provide additional services to our users in European Weather Cloud by simply integrating Terraform into our pipelines. We created for our users some blueprints in form of Terraform files for them to deploy hassle-free operations on their cloud. For example, on the right-hand side, you can see we are using a Rancher cluster template resource coming from Rancher provider in Terraform without even developing a module or anything additional on top to create a European Weather Cloud Kubernetes service for the end users. And we kept doing that. We created different library items for our users to deploy on European Weather Cloud to make them enable additional services on top. One example was, as I told, Kubernetes server, but the others are DAS cluster, the UMSAT software stack, like Data Tailor and other stuff that I mentioned in my previous slides, and HT Condor batch processing environment. But I also would like to highlight its effect on simplified operations for engineers like myself. Because as soon as we start working with multi-cloud, we realize that multi-cloud also means multi-trouble. Multi-trouble when it comes to the operations, multi-trouble when it comes to have consistent configuration on multiple cloud infrastructure. And by simply integrating Terraform to our existing pipelines, we managed to build a machinery that can test, plan, and deploy infrastructure and infrastructure changes on the multi-cloud infrastructure that we have available. So as an example, you can see on the right-hand side that I was simply upgrading a Kubernetes version. And this commit triggered a change in my pipeline, in my CI/CD pipeline, which basically runs Terraform in the backend to do the planning and deployment after an approval, which is a huge increase on operations, reducing the overall overheat. We also managed to solve some everlasting issues, such as secret managements in our pipelines, with integrating Terraform with other available tools and other HashiCorp products, such as HashiCorp Vault. Terraform provides an extensive list of integrations that you can integrate your pipeline with, and we were already using some tools like Ansible, GitLab CI/CD, external secrets operator to manage multiple things in our ecosystem. So probably you already know the secrets in CI/CD is a big topic, and I think you can all relate the challenges that you can face. But integrating Terraform with Vault and other tools that we have in the ecosystem enable us to solve the secret management, which was a big problem that I mentioned earlier, but also provided an opportunity for us to provide better service to our end users, such as managed Kubernetes, integration with OpenStack in form of cloud computing resources, because that will require you to share the cloud credentials in a secure channel. You can see in the right-hand side down below. And Vault enabled us in close collaboration with Terraform to do just that. Well, after doing all that, we had an idea of replicable multi-cloud automation blueprints for Earth observation community. And a European Union Horizon project called Earth Observation for European Union, EU for EU for short, provided us an opportunity to cater the much needed Terraform scripts in form of modules targeted to the Earth observation community. You can see some screenshots on the right-hand side, and these modules, I must say, are still in progress, and we are trying to make them available for all Earth observation community to use in hopes of allowing further collaboration to build greater things. One example is the use case that we had in training at BITS conference, multi-cloud data proximate training. We already mentioned about the multi-cloud data proximate prototype that we had earlier, but Big Data in Space, or BITS for short, conference allowed us to have a 2-hour demonstration and tutorial on multi-data proximate compute prototype, this time with cloud native data formats and multiple cloud backends. So Terraform and with some extent Vault allowed us to build this training platform and build and manage this training platform required to showcase this use case. Well, to give you an idea, we hosted 30 registered and some unregistered users popped up during the training, carrying on computationally demanding tasks on 2 different clouds, EWC, European Weather Cloud, and VKO. Each user had 1 worker per cloud, hence 2 workers, and access to the cloud native data format. In this case, it was ZAR. This totaled around 200 vCPUs and 800 gigabytes of RAM. And you can see in the right-hand side a snippet from a Juniper notebook that we have. I will share the links in the next slide, where a user can easily create a cluster, a Dask cluster, spawning out in 2 different cloud infrastructure with the resources available to consume them. And I am not a scientist, and you can learn more about the science behind all that in the link that I'm showing here. But the whole calculation took around 10 minutes. And as I am told, this would be impossible to carry out with the traditional data access and processing methods. This already showed us how the leap can be if we use and utilize the correct tools to build such a platform. And I must tell you guys, it was powered by Terraform. So the machinery behind it to host this training use case was Terraform integrated with a couple of other things in form of modules and CI/CD pipelines. So we had Terraform and Ansible integrated together with some extent with Vault to build this training platform, scrap it, rebuild it again, and extend if needed. This kind of flexibility is impossible to achieve with traditional manual way of doing things. And Terraform provided the building tools that were necessary to build this kind of a training use case for Earth observation community. So where next? I think to infinity and beyond. I believe, especially after the training session at BITS, that multi-cloud architecture in combination with cloud-native data formats is the future for Earth observation data processing. And Terraform can enable us to develop examples of such user-driven cloud-native workflows across multiple, either public or community clouds, cloud agnostic. And we are committed to improve our Terraform modules so that Earth observation community may create even more impressive things. Lastly, I would like to leave left some references and links to Clink. You can gather more information about the topics that I mentioned here. And if you have some questions, I am available at the chat. And thank you very much for your time, and have a nice rest of the session. Goodbye.
Wow. Okay, that was absolutely. I mean, and let's be honest. Multi-cloud is hard. Multi-cloud is always hard. Terraform makes it easier, but it's still hard, right? But now going up to multi-cloud, like 3 different clouds, and then bringing data not from Earth, but like from satellites that are technically above the clouds, not just technically, they are, obviously. That's quite something. So I looked into their mission, right? Because I was like, okay, this is really cool. I like this. This is very cool. Like, you're using satellites that are called Sentinels, which, I mean, beautiful name. You know, like, I like this. You're monitoring the atmosphere, climate, land masses, oceans, and you know what the best part is? If you go to the link, will drop in the comments. You get all the pictures. Like, you get all the wallpapers out of this. The data itself, very important for much smarter people than me, but I like the pictures.
Nice. I figured you would like the pictures. I'm not surprised, Kareem.
There's some amazing stuff in there.
Exactly. Arman, that talk was amazing. Thank you very, very much. Now we're going on to our last speaker, Nat Bellavance, one of our beloved HashiCorp ambassadors. And Nat has created a CLI in Go called terahash to generate module log files. Now, I'm really excited to learn more about your journey and how you've built it. So Nat, the stage is yours.
Everyone, thanks for joining my talk about a tool that I developed that hopefully addresses a need that I saw in the Terraform ecosystem. I'm Ned Bellavance, and this is about terahash. So what is it? Terahash is a standalone CLI tool that I wrote in Go that's meant to help with verifying the provenance and contents of modules that are used in your Terraform configuration. My goal with the project was to help users lock down the module versions used in their code and the contents of those modules. Now, before I get into the tool proper and show you how it works, I'd like to explain the challenge I saw out there and how I went about solving it. And that brings me to the quest for stability. We all want our deployments to be as stable and reliable as possible. Infrastructure surprises are never fun. And since we're all using code to deploy and manage our infrastructure, what we're aiming to do is reduce the number of surprises that we're subjected to. Some of those surprises are not under our control. They're out of our hands. Services like Azure Active Directory or Amazon S3, they have outages. They go down. DNS records can be pointed to the wrong thing. In fact, I think that was the cause of at least one of those service outages. And BGP routes can get sent to some poor ISP in Pennsylvania that gets completely overloaded. As a totally random example, actually, it's a pretty fun, interesting story. I won't say fun, an interesting story if you want to dig into it. But those things are outside of our control. So what we aim to do is to stabilize as many things as possible that are under our control. And when it comes to using Terraform, that includes the contents of our Terraform code and the manner of execution of that code. So when we're thinking about code execution as it pertains to Terraform, there's two key components involved. There's the Terraform binary itself, and then there's the provider plugins. If you want to control the version of Terraform you're using, you can do that in your code by using the required version argument inside of the Terraform block. You can say, I only accept this version of the Terraform binary, or it has to be within a particular range. You can control the version of the Terraform provider plugins by using the required providers block that also goes inside the Terraform block. Now that covers the execution portion, the bits that actually go and talk to the cloud services and do the rendering of your Terraform configuration. You can control both of those aspects. But what about the actual content of the code itself? Hopefully, you're checking your code into source control and you're versioning it as part of your deployment process. Changes that happen to your code can be viewed by comparing it to the previous checked-in version. So you can always do a diff and see what has changed based off of the last commit. You can also preview the impact of those changes by running an execution plan using Terraform. In fact, that's one of the main selling points of Terraform, right? Is you can see what changes are going to be made before they're actually made, enhancing that stability and control. All the code that you put into your root module is managed directly by you. You're writing the code, you're checking it into version control, at least I hope you're checking it into version control. So you should feel confident about that aspect of the code. However, I bet more than a few of you are using child modules. And the code for those child modules, that might not be under your control. So what can you do then? Well, let's talk about how you get modules in the first place, and then what we can do to protect ourselves against the contents of those modules. Modules can broadly be sourced from one of three locations. You can get modules from the local file system. That could be a subdirectory in your root module, or it could be a directory somewhere else on your file system. That's up to you. You can get modules from a source control repository. Actually, you can get a module from pretty much any HTTPS that will serve up some files, but we're going to focus on source control for this. Or you can get it from a module registry, and that could be the public Terraform registry, or that could be a private module registry. So let's cover the current options and how you can control the module contents, and if you can control the module contents for each one. If you're using a locally sourced module, then it could be living in the same code repository as your root module, and then you have the same version control mechanisms available. If it's living in another repository or not living in a repository at all, then you might not be able to maintain control over what's in that module. When a module has been sourced from source control, you're getting it from a version control repository, Terraform by default will grab the latest commit from the default branch unless you tell it otherwise. You can tell it otherwise by appending a query string to the end of your source URL. And you can do that to reference things like specific Git tags or a commit ID. Now, depending on how specific you get, you might be able to ensure you're getting the same version of code that you think you are. If you're using a commit ID, it's pretty hard to forge commit IDs. So you can feel pretty confident that if you're sourcing it by commit ID, you're good to go. But if you're doing it by Git tags, you don't have as much control as you might think. And we'll dig into that more in a moment. The last option is modules sourced from a registry. And when you source modules from a registry, they support the use of the version argument. And I highly recommend that you use the version argument, and specifically that you pin it to the exact major, minor, and patch version just to prevent any issues. But the point is that the version argument, what it's actually doing in the background, requires understanding how modules are published to a registry. And essentially, the registry is pointing back at some sort of source control repository. And in that repository, you are going to cut release tags. And those release tags signal to the registry that a new version of the module is available and to publish that version of the module. So when you're specifying a version argument inside of your module block, you're kind of indirectly referencing the release tags for that module, whatever source control repository it resides in. So that still leaves you at the mercy of the person maintaining the module and the repository. What do I mean? Let's take this example. So let's say I have a module called Terraform Azure RM Networking, which I do. And my current release tag is 1.0.4. I just released that today. Woohoo! Now, as the maintainer, I can go delete this release. And then I can alter the contents of the files and draft a new release and choose the exact same tag for that release. The contents are going to be different and the commit ID will be different, but the release tag won't be different. So if you're consuming my module, you could be completely unaware of the change. Maybe you'd catch that change when running a Terraform plan, but if I'm sufficiently sneaky, I might be able to put something in that you don't notice, and that could be bad. Now, if you're someone who wants to control the contents of your code, all of it, if possible, you need a way to verify that the contents of your modules is the same from run to run and be alerted if it does change, especially if you have a security team that's vetting modules and saying this version of the module is approved for use in your organization. And so that's what terahash was created to do. The tool is similar in nature to what Terraform does natively for provider versions with the provider lock file. So if you're not super familiar with that, I'm just going to dig into that for a second. When you run Terraform init for the very first time on a new Terraform config, Terraform enumerates, well, it does a few things. It pulls down the modules that you're using and stores them locally if they're from a remote location. It initializes the state backend, and then it looks at all the providers that are used by your root module and those child modules that you're using, and it goes and grabs the latest version of the providers that meet the requirements of your version constraints. When it does that, once it has those provider plugins, Terraform creates a file called .terraform.lock.hcl, and that contains each provider used by the configuration, including the version constraint, and the hash of the provider. The hash is used to verify that the hash of the plugin matches the hash published by the registry for a given release, and that helps to ensure that the local plugin hasn't been tampered with or nothing's gone wrong with its checksum in transit. Now, the big idea here, is that you take this Terraform provider lock file and check it into source control along with the rest of your Terraform code. When an automation system or another team member pulls the code down and runs Terraform init, Terraform will find that lock file and it will use the exact versions of the provider plugins that are recorded in that file. Terraform won't use a newer version of the plugin, And if a maintainer of the plugin tried to sneak in an altered version under the same number of the provider, the hashes would no longer line up and Terraform would throw an error. So if somehow the maintainer of a particular provider plugin was compromised and someone tried to sneak in some weird code in there, that would be caught by the fact that the hashes no longer line up. So if you have a security team that is verifying providers and approving them and specific versions of them, you have a protection mechanism there. The other idea behind that is that you get a consistent experience because everybody who's running the Terraform code is using the same provider plugins everywhere. Terahash is meant to provide similar functionality to the provider lock file, but for modules. So let's jump into a demo and see how this thing works. In my demo environment, I have a Terraform configuration that uses the Azure RM provider and 3 modules. The first module uses the Azure VNet module to create an Azure virtual network. Kind of obvious, right? It's sourced from the Terraform public registry, and it's pinned to a specific version. In this case, it is pinned to version 4.0.0. The second module block I have in my configuration is sourced from a local location. It's using a module that's in the subdirectory modules/server. And there's no version because local modules don't support versioning. The third module is sourced directly from GitHub, and it's using a release tag. So this is actually the label module from Cloud Posse, but rather than grabbing it from the Terraform registry, I'm grabbing it directly from the source repository where it exists. And I'm using this ref equals tags/o.24.0 to get that specific release of this module. And then the rest of the arguments are just the arguments you need for that module. Now, I'll start by pulling up the terminal, and I'm going to run terraform init to initialize my configuration. This is going to create a few things in my file structure. It creates a .terraform directory, and it also creates the lock file over on the left. Let's explore what happens with the .terraform directory. Inside the .terraform directory, there's now a modules directory, and inside of there is a modules.json file. So let me hide the terminal, and I'm going to prettify this JSON because it's pretty hard to read in that format. All right, there we go. So this module file has a reference to each module in the configuration, including the root module, and it records the key, which is the module block name, as well as the source and the directory, and if versioning is supported, it also includes the version. Terahash essentially parses this modules.json file to create the necessary lock file. Now, the root module is ignored since we control that code and don't need a hash for it. Although, if you'd like to include the root module as an option, you could file an issue. By default, Terahash will process all the other modules, including the local and remotely sourced modules. So I'm going to pull up the terminal, and before I run any specific commands, I'll simply run Terahash by itself. When you do that, it will print out how you can use Terahash along with the available commands. Now I'm going to run Terahash version to see what the current version is. And right now it's 0.1.0. If you look at the available commands, there's 3 commands that I want to pull your attention to. The first is init. Init does kind of what Terraform init does. It is what actually creates the mod lock file if one doesn't already exist. So it's the first thing you're going to run when you want to run Terahash. The second is check. Check determines if the lock file matches the configuration. And then the upgrade command will update the contents of the lock file to match what's in your configuration. And it requires approval to do so. So the first step in our process is to actually create the lock file. And I'm going to do that by running Terahash init. So let me clear out this view and run Terahash init. There we go. It has given me some output in the terminal. It tells me that it found 3 different modules, and then it also lists out some information in a table, which is a little hard to read when we're zoomed in this much, but if you zoom out a little, the table does line up a little bit nicer. And then down at the bottom, it provides a summary of what it did. It added 3 modules to the lock file. Now, if we look in our file structure, there's now a terraform.module.lock.hcl file. Let's take a look at its contents. Now, looking in the contents, each module has an entry in here, and that entry includes the key, which is the name label, the source where it came from, the version, the directory where it came from, and a hash that was computed based on the contents of that module. Let's see what happens if I start making changes to my Terraform code. I'll go into the main.tf file, and I'm going to make a few alterations here. I'm going to start by changing the version of the VNet from 4.0.0 to 4.1.0. So I'm pulling a different version of the module from the repository. And then for my second module block, since this isn't being pulled from a remote location and doesn't support versioning, I'm just going to go into the main.tf file for that. And the only thing in here is an output, so I'll change the output from Burrito Grande to Nacho Libre. All right, so I've altered the contents of that module. And then going back to my main.tf, for the one that I'm grabbing from the GitHub repository, I'm going to change the ref tag from o.24.0 to o.25.0. Okay, now I've made all of these changes. The next thing I need to do is run Terraform init again. And the reason I need to do that is Terraform init is going to grab the contents of the newer version of the modules that I'm sourcing remotely. And then it's going to update the modules.json file with that information. Now that I've done that, I can run terahash check, and terahash check will check and see if the contents of the modules matches up with what is in my lock file. So I'll run terahash check, and unsurprisingly, 3 of my modules don't match, and it exits with an error saying non-matching or missing modules found in the configuration. That is what I would expect. And in fact, that's what I want to happen. I want terahash to error out when it checks to see if what I have in the lock file matches up to what's in my modules subdirectory. Okay, so let's say I want to update my lock file. I made those changes to the code. They're changes I have vetted, and I want to have my lock file show those changes. Well, to do that, we run terahash upgrade. And that will go through the same process of checking and seeing what the differences are. And then it will give me a summary of the changes it wants to make to my lock file, and then ask me to confirm those changes. I'll enter yes, and now those changes have been made. You can also skip the prompt by adding the auto approve flag if you'd like, just like you do with Terraform. If I now run terahash check again, do that now. Now it comes back that all modules match and it does not error out. It exits gracefully, and that's what I would expect. So how would I implement this in an automation scenario? Here's how I see it. You would still develop your configuration locally like you usually do. Then before checking your code into source control, you would run terahash init, assuming that you don't have an existing module lock file. You'd run terahash init to create that module lock file, and then you would check that file into source control with the rest of your code. In your automation pipeline, after you probably have a pretty standard automation pipeline, and one of the first things it probably does is grab the contents of your repository and then run Terraform init. You would keep that part just as it is now, but then after init completes, you would have terahash check run. And then terahash check will see if there's any differences in the module contents versus the module lock file. If differences are detected, then terahash will error out, and you can choose to halt the deployment process or add a warning of some kind to your pipeline, whatever makes the most sense for you. If no differences are found, then the pipeline continues unabated. When you want to upgrade the version of a module or or the contents of one of your local modules. Locally, you'll run terahash upgrade after you've made your code changes, and then you will commit that updated module lock file into source control along with whatever changes you made to your code. That's pretty much it. It's fairly straightforward. You've now asserted control over the module code that was previously outside of your purview. That protects you against other people making unmanaged or unwanted changes. Some of you might be wondering, that's a pretty cool idea, Ned. Why not integrate this directly into Terraform instead of writing a separate tool? After all, they have the whole provider lock file thing. Why wouldn't you just add this to Terraform? That is a fair question, and I do have a few reasons for that. First and foremost, I just started learning Go like 6 weeks ago, and I really wanted to build something from scratch. The lessons I was learning were fairly abstract. I mean, yeah, I was like making a basic grocery app, that kind of thing, but I wanted to apply it to a tool that I actually would be interested in using and maintaining. So terahash was a way of doing that. The other thing is I looked at the code base for Terraform, and now I understand it a little bit more because I've gotten my hooks into Go, but it is still overwhelming. And I just wanted to build something separate that I could understand. The other reason is that getting a new feature into Terraform is not going to be a quick process. It's going to take a while. I would need to open an issue and talk to the maintainers of Terraform, and we'd have to figure out whether this is something that they actually want, how they want to implement it, and then they'd have to dedicate hours to helping me implement that new feature. I'm not saying that HashiCorp wouldn't do it, and maybe someday they will, but it would have required a decent amount of back and forth. And the third reason is that I want my tool to be usable to people who are using Terraform and OpenTofu. And I'm worried that if I contributed the code directly to Terraform, I wouldn't be able to add that same feature and functionality to OpenTofu. And so thus we have a separate tiny tool that does one thing, I hope, pretty well. So what's the current status? Right now, I just released version 0.1.0 of the tool, like a week ago. So hopefully that gives you an idea of how mature or immature the project is. It absolutely does what it says on the tin. It will create that module lock file and check the contents of your modules against that lock file. It does what it says. But I think there's a lot of room for small improvements here and there in terms of usability and features. Could you use it today in your automation pipeline? I think so. You should do your own due diligence, code scanning, look through it, all that kind of jazz. Maybe have your security team vetted if that's your kind of thing. But I think it's ready to use right now. Just bear in mind there might be some breaking changes later. Now, personally, I have a list of things I'd like to add to the tool, including better formatting for the output. I wish those tables lined up nicely, although that's pretty hard to do in a terminal that's resizable. I would like support for environment variables for some of the argument inputs. I'd like to add selective upgrades for the module and also just give a more robust explanation when you have non-matching modules. What about those modules didn't match, and what does that mean for you? If that sounds interesting, can you contribute? Yes, you can. This is an open source project on GitHub, and I welcome suggestions, issues, contributions. Some people have already contributed to the project, and to those people, thank you so much. Whether it was opening an issue or actually contributing code, I've had both, and it's an awesome feeling. I want this tool to be as useful as possible to the community, and it's such an early stage at the tool that I'm happy to consider any changes, whether they're minor or major. Even if you don't want to contribute, I'd love to have others take the tool for a spin. Let me know what you think. You can find the project on my GitHub repository. It's ned1313/terahash, and I'm sure a link will be included somewhere. If you want to reach out to me directly, you can hit up nedinthecloud.com or just ping me on LinkedIn. I'm pretty easy to find. Thank you to everyone for watching, and thank you to HashiCorp for putting on HashiTalks Build. Special shout out to Jasmine and Alexandra for encouraging me to present on this topic. I was a little nervous since I'm not a Go developer, but I guess now I kind of am. All right, well, that's going to do it for me. Thanks again, everyone, and enjoy the rest of the event.
Nat, you definitely are a Go developer. Building this as your first tool is amazing. I can't wait for what else is coming. Thank you for that awesome talk and tool. I just installed it. Well, what are your thoughts, Graham?
I think anything that makes it harder for a supply chain attack to take place is always worth looking into. So I'm all about this.
Nice. Nat, thank you very much. Now, we've reached the end of day one of HashiTalks build. If you want to rewatch the sessions at a later time, they will be available on the HashiCorp YouTube channel in the coming weeks. Looking back, Kareem, I think we had a pretty exciting day, right?
Definitely. I mean, so much good stuff. It's I think the beauty of build every year is that it's so hard to like pick your favorite. It's like we review the day, we look back on day one, we'll look back on day two tomorrow. It's gonna be like, what was your favorite talk? It's hard, and that's a good problem. We want this to be useful for you. We want it to be useful for us. So that's it has to be good content, and I think we did that.
Exactly. Creative people with creative solutions. And yeah, we talked about a lot of things, right? We talked about what makes a good UX, self-service infrastructure, migrating state between AWS CC and AWS providers, surviving a monorepo mess, and how you go about structuring your HTTP Terraform organization, as well as monitoring it, Terraform's testing framework, and how Terraform plays a key role in that Earth observability, Earth observation community, and how you can fingerprint modules using terahash. Now, like I said, I couldn't pick a favorite of today's sessions because they were all really good, and I'm sure Kareem has the same. But
absolutely.
Kareem and I are going to wave goodbye to you in a moment. But don't be sad. Tomorrow is going to be another day of HashiTalks build, hosted by our HashiCorp ambassador, Pado Arfizu, and our very own Martin Smith, principal site reliability engineer at HashiCorp. And with that, any closing notes from you, Kareem?
Just stay tuned for tomorrow. It's going to be more awesome content, more valuable content. Make sure you load up on coffee if that's your thing. Otherwise, white tea will also work. And be here. Click the notify button. Don't miss out.
Exactly. And with that, you all have been wonderful, and we'll see you tomorrow. Bye-bye.